see what's on the screen?
Yep.
Okay, are we waiting for anyone else, or can we start? Okay, we can wait about 2 minutes and then get started.
Awesome.
Okay, so we're only missing one person. If everyone can see the screen, I think we can get started. Whoever needs to come in can come in due course of time. I'm quite excited to share what's the second part of this talk, because when I was learning the calculus of variations, I found it quite difficult to go through. Did someone new join? Okay. Yeah, I think everyone's here.
Yep.
Okay, great. Let's get started. Okay, so for those of you who were here last time, I think everyone, apart from a couple of people who were here last time, we said the goal of relativity is to try to understand what stays the same and what changes when we move across frames of reference. Which is to say that if I'm describing an object, if I'm standing still, if I'm moving in a car, right? What can I say about this object that everyone who's looking at it will agree? If there's something about this object that changes when I look at it differently, then that's not a fundamental truth. We want to describe the laws of physics in a way that everyone, whether you're standing still, whether you're in a car, whether you're standing on the moon and watching, everyone should agree with the physics that you're talking about. Okay, so we discussed that last time. And I'm going to start by talking about scalars and vectors and a different way of thinking about them. And from there, we're going to move on. So the first thing that I want you to understand is, so far when we've been discussing the concept of what a scalar is and the concept of what a vector is, in school, we've been taught that a scalar is just something that has a magnitude, right? Whereas a vector is something that has a magnitude and a direction. And today, I'm going to try and tell you why this first approach to what a scalar is and the first approach to what a vector is in school is fun, but it's not very useful, and it doesn't tell us there are better ways to think about this that give us more profound consequences. Is everyone here? Did we lose someone? Did someone get disconnected? We have 12. How many did we have to start? Can everyone hear me?
Yeah, we can hear you. We can hear.
Okay, great. Right. So in the beginning, we were taught to think about scalars as something that has a magnitude and a vector that has a magnitude and a direction. But we can quickly see that this essentially doesn't apply. For example, if I call a vector just a collection of quantities where I can have apples, bananas, and I say that they have a certain direction, this makes no sense, right? Like just calling something a vector just because it has a direction and a magnitude is incomplete. And the true story of what a vector is, and something that's useful to think about, is a vector is any kind of arrow, right? Which, when I look at it from different frames of reference, whether I'm in a car, right? How this looks to me, I want a sort of law that tells me what this vector looks like to me, which is to say that a vector should not only be something with a magnitude and a direction, but it should give me some sort of understanding in how people from different frames of reference see this vector. Right? So that's essentially how we want to be thinking about vectors. A vector is something that comes along with it, a prescribed law for understanding how, for example, X, Y, Z transforms to some other X, Y, and Z. And someone in the car will say, well, this is the vector that I'm seeing. And if you're standing, you're saying, no, well, this is the vector that I'm seeing, right? So we need a prescription which changes each coordinate and maps each coordinate to the next one. So in that sense, a vector is something that transforms in a particular way. And the way that this transforms is what we define to be a vector. Is this clear? It's just a different take on the same concept. We're not thinking about magnitude or direction anymore, but we're saying how things transform fundamentally from one reference frame or another defines what that vector is. Okay, so a vector is something that changes. It could be longer, it could be shorter, it could be pointed in a different way, depending on the direction that you're looking at it. Okay, whereas a scalar is something that does not change. If I have a scalar, let's say, so we can think of the examples for the vectors that we're talking about don't change, which is to say that if you have the velocity of a particle or a box or anything that's moving, we can understand what this velocity looks like in a new frame of reference. So the examples don't change. I want you guys to think about the examples for what scalars could be, because this is something that I want you to think and relate to examples in the real world. I'm asking you to give me an example of something that doesn't change, whether we look at it from a moving perspective. If we hang upside down from the ceiling and look at something, the question we're asking is what doesn't change? So could anyone give me an example of what this scalar could be? Anyone?
Shape of a spherical ball.
Shape of a ball is not, it turns out not to be a scalar, because it turns out when you move really quickly, the ball appears squished. So
Okay, fine.
Shape of something isn't a good indicator of.
Probably like a symmetric quantity.
Even a symmetric quantity will change. It gets squished in one direction and elongated in another. So something that's symmetric to one observer isn't symmetric to another one. So,
but how do we say that scalars doesn't change? We define the change based on the scalars, right? So
no, so
with
I'm
numbers.
saying with numbers, but okay. So the point I'm trying to make is numbers and numbering systems are all figments of our imagination. Numbers are just like the equator that we draw on the globe. And a picture that I want to get used to drawing is the real world would look like this. And there could be a ball or a car that's moving. And what we are doing is over this, we're inlaying our own coordinate systems. That's what we're doing. This is our construction. Whereas someone else who's hanging upside down from the ceiling will say, no, the way I'm going to draw my coordinates is like this. And the question we're essentially asking is, how does this car look to the person who's drawn the car in the blue coordinates? And how does it look when you describe the car in any other kind of coordinates? And are there quantities that don't change? Well, if you have a vector, it's something that you have a transformation law going from this to this. I have an understanding of how vectors change. The real world examples that I'm asking you to think about are quantities that what we call scalars are things that don't change depending on the frame of reference that we look at. And for this course that we're doing now, when I say frame of reference, I mean, if you have a friend who's hanging upside down from the ceiling, would they agree with what you're saying? And if there's someone who's moving in a car or a really, really fast plane, would they agree on what you're saying? So I'm going to give you one quick example of what a scalar could be. And the first thing is to say mass. The mass, or if our terms and conditions apply, the square of the mass of any particular object does not change, depending on the frame of reference that we're looking, whether it's someone who's standing still or someone going in a car. Clear to everyone? Like, this is a pretty easy argument to follow. Unlike a vector, which may change the direction in which it's pointing, the mass will always be the same. The square of the mass will always be the same to the observer that's watching it. Okay? And now I'm going to start by explaining to you that essentially the goal of all relativity is to...
Chinmaya, I have a doubt over here. Like, you say that mass doesn't change, but we know that mass increases when we travel near, like, greater than 10% of speed of light, right? Relativistic mass. there's a change in the observed mass, right? So we can't say that it doesn't change.
Okay, I can get back to answering that question at the end of this session, but I'm going to explain to you that the real relativistic equation isn't the rest mass that you're talking about. Okay, so I should actually say the rest mass stays the same, but
yeah, rest mass stays the same.
The real equation is this. And this is actually the invariant that you talk about. And I can get back to answering this at a later time, because I don't want to digress right now. We're gonna talk about the Lorenz transformation first. Another example I can tell you is if we draw a coordinate system, and let's work with this now. So remember, the way that I'm doing this is I'm picturing the world like this. And actually, you can hold me to that. I can prove to you later that this quantity doesn't change, and it's an invariant, and the relativistic equation that governs it is this particular one, and this is an invariant. The point I'm trying to make right now is that if I have any particular object, let's take a vector like this, right? I can draw a set of coordinates that look like this, right? My friend who's hanging off the ceiling would say that no, the way that I draw my coordinates across this world are like this. Okay, and the difference between my coordinates and this person's coordinates is labeled by theta. So the first thing I'm going to do to you is to tell you that what we're looking for right now is that when I change coordinates to a different frame of reference, what we find the length of a vector, that's something that's a scalar. And that's something that doesn't change. That the vector might look different, it might have a different orientation, but the length of this particular vector does not change depending on the observer that looks at it. And the proof of this is particularly simple, which is that if I label my old coordinates by x and y, and I label the new coordinates as x prime and y prime, okay? The coordinates that are the new coordinates can be written in the old one in this form. I can write it as x prime is x cos theta minus y sine theta. Y prime is y cos theta plus x sine theta. Okay, this is essentially how I relate my new coordinate to the old one. And if you guys remember the conversation from last time, I told you that anytime you have a transformation of any kind where you have different frames of reference, this transformation in me going from one frame to another is always represented by some matrix. Okay, so the same set of new coordinates, I can write it as some sort of column vector, a particular matrix, sine theta, cos theta, acting on my x and y coordinates. Has everyone seen a matrix like this before? Is this the first time anyone's seeing this? Have you all seen this before?
Yes, we have seen that.
Okay, you guys have seen this before. So
why did you ask that question? Because it's a pretty simple matrix. We have.
Sorry?
Actually, is there any specific reason for you asking that question? Because it's a pretty simple matrix, but I don't find anything different in that. But yet you asked the question of whether we saw that matrix.
Just to know if you're familiar with this, because what I'm going to argue to you first is that this matrix here, when I input the value of theta, tells me how I can go rotating my coordinate system anywhere in this direction. Like I can have something like this, I can have something like this. Essentially, whatever my angle theta is, I have a way of representing my old and new coordinates, right? So my vector, my initial vector here will look very different depending on what x prime is compared to what x is. Because if you remember, a vector is written in terms of a basis, right? Like this I hat and what a j hat is. These two I hat and j hat change depending on whether you use polar coordinates, whether you use orthonormal coordinates like x and y Cartesian, right? So the vector itself looks different. What I'm going to argue to you is that the radius of this vector doesn't change. So if you look at this and I ask what the distance is here. Right? I can use the Pythagorean theorem to say that x squared plus y squared is what I call the length of this vector. Okay? And if I ask what this looks like in the new coordinates, well, that would be here. If you look at this particular equation, and I substitute that in here, you have x squared cos squared theta plus y squared sine squared theta minus 2xy sine cos. And then here I got x squared sine squared theta, y squared cos squared theta plus 2xy sine theta cos theta. And if I add what x and y are, I find that these two terms cancel. And I've got x squared into y squared into sine squared theta plus cos squared theta. And since both of these are 1, I find that the length of this vector in my new coordinate system is the same as what I had earlier. Right? I'm hoping this is comfortable to all of you. You've all done a similar exercise in the past. It's a fairly easy matrix to work with, as you said. But the reason I'm telling you about this is because in relativity, if you remember what we spoke about last time, the vectors that we start with aren't the same as the normal vectors you deal with in 3 dimensions. So in special relativity, right, we say that the vector under question is a 4 vector now, which now has a time coordinate. And there are many examples of these 4 vectors. Okay, this is one example. Another example is called the position 4 vector. There's another one called the momentum 4 vector, which combines the energy and the momentum in 3 directions. Okay, and the reason I'm telling you about this is because if you notice, we can split this 4 vector into something that's a scalar along with a 3 vector. Right? Is everyone comfortable with what we've discussed so far? The goal of all of physics right now is just like how I showed you earlier, where we had the length of a vector, which we called r square, that didn't change. It didn't change if you looked at it from the x and y coordinate system, or whether you looked at it from x prime and y prime, no matter what the angle theta was. Like theta could be small, theta could be big, you could rotate it any which way you want, but the length of this vector stays the same. Right? Everyone is clear with that?
Okay, what is it E over there in the momentum 4 vector?
This could be the energy.
Okay, fine.
And if you guys pay attention, last time, if you remember, I told you this time, it's not really time, we have a factor of c there. Because if you have c and t, that makes all of this into the units of length. C times t has units of length, these have units of length. You can ask the same question here and you'll find that there's a factor of c somewhere. I think it's pxc, pyc. Like there are factors of c in here for you to write it this way, right? So if you remember what we spoke about last time, we said that the thing that doesn't change in relativity, right? Just like how you have so remember, when I say something that doesn't change, you must immediately in your head think scalar. Okay? And in normal geometry, we found that the scalar that we want to talk about is the length of the vector. Right? And at the end of the lecture last time, we said that what we're looking for that doesn't change, the invariant in special relativity, is this thing called the space-time interval. Right? Does everyone remember this? We spoke about something called the space-time interval, and we said that the space-time interval is something that does not change. So we're going to talk about that. And I want to do a quick digression soon about a particular graph that you all saw in the chat earlier, where someone said, you can talk about the sine and cosine waves as being interpreted around a circle. And I want to talk about that soon and explain to you why you can think about the space-time interval in the same light. Okay? So all I wanted to tell you right now is the fundamental law of relativity is that the laws of physics are preserved under Lorenz transformation. Okay? This is the fundamental theorem of special relativity which you have to be thinking about when you go on to study other theories. So this essentially tells us, if you remember what we studied last time, we found that if you talk about the length of an interval, we mean the space-time interval, the distance between two events, right? And we said that every observer, regardless of where they are, will agree that the speed of light is the same. And the consequence for that is that the only allowed transformations between different observers preserves this, right? And they all agree on what this length is, which is to say that whatever theory in the future you build, whether that's electrodynamics, whether it's quantum mechanics, you need to first prescribe for me a way that different observers talk about the same physics or the same observables that you're talking about in your theory. Okay, and this is something that isn't there in quantum mechanics. It just isn't there. We don't have a description of quantum mechanics that's relativistic. When you go towards relativistic quantum mechanics, you have something called QFT. So I just want to do a quick diagram of what the roadmap of physics looks like. And the realm of physics is that when you talk about classical mechanics, all your pendulum problems, all of the stuff like that, you're assuming things aren't like small, they're normal sized, whatever normal means, meaning h bar isn't relevant. And you say these things aren't fast moving, which is that the speed of light, you're not getting anywhere close to it. The speed of light is, for your intents and purposes, it's infinity. Okay? And if you have, if you move to the realm of things being small, sorry, I think you can see it now. Yeah, when you move to the realm of things being small, you say that's what quantum mechanics is. If you say that we're now going to move at high speed and talk about the physics there, that's what special relativity and general relativity come down to. And if you're looking for something that's small and fast moving, that's what QFT. That's where you want to be looking at quantum gravity. Okay, so the reason that we're talking about special relativity and this invariance of space-time intervals is that anytime you leave the realm of what classical mechanics is and you try to understand how theories behave when you move fast, you have to describe them in a way that leaves your space-time interval untouched. So today's session, in the first half, we're going to be talking about what these transformations look like and how they preserve the space-time interval. Okay, so last time, the question that I got from everyone was this. The space-time interval was defined as this. Does everyone remember this? Does anyone remember this as the fundamental equation that we studied last time?
Yeah, we remember it.
Okay, so I'm going to do two things for you first. The first one is to explain why there's a minus sign in t squared. And the second thing we're going to be looking at is why does this have anything to do with that diagram with the that we spoke about last time? What does this have anything to do with the shape? Okay. The first thing that we want to do is say that if I had a ray of light, right? What I want to do is understand how far this ray of light has traveled in space. And the way I can do this is that if I have an event here at x and another event at y, or I should label it as x1 and x2, right? I can say the distance between me, this ray of light, let's say me setting off a flashlight and you maybe 3 kilometers away receiving it, the distance between this is just the distance formula, right? Which is this thing. And I can do the same thing for z, right? And I told you last time what we're going to do is every time we talk about an observer, they are the origin. You look at the world from your own origin. So we said that for all intents and purposes, there doesn't need to be a second y coordinate here. And we said the distance between 2 points or 2 events is just the square root of x squared plus y squared plus z squared. Right? Everyone's clear with this?
Yeah, that was delta squared. That's what I was going to say.
Yeah. So the key insight that Einstein had and what we call space-time is to say that it's not just an event that's separated in space, but when you travel with the speed of light, you're also separated in an instant of time. the time that it takes for light to travel from one point to the other. And if light is traveling at the speed c, right, the distance that the light covers is just the time taken by the light to travel from one point to the other. This c times t is a unit of distance. And the argument that Einstein did and Minkowski did in spacetime is to say that the distance between two events physically is the same as the distance traversed by light, c times t. And if you equate the two, we get this. Equals x squared plus y squared plus z squared. Right? And this is what we call the spacetime interval. So the first thing that we see is that if you're talking about light, for two people, if you have two different people, will always agree on what the spacetime interval is, right? And for light, the spacetime interval is 0. That's the first important result. So if you have a light ring, this is what it looks like. Is everyone clear on this? Do you see why there's a minus sign here? It's just simply saying that the distance that it takes between two events not only can be expressed in terms of a distance in space, but also it has to be a distance in time. Is this clear?
Yeah.
Yep.
Okay, good. So the second thing, which is what does this have to do with the light cone? I think there's a really nice explanation for it, which ties into the earlier explanation for someone had posted a graph saying that a sine wave, well, it looks like this, right? And a cosine wave, for example, whatever, looks like that. So can one of you who hasn't spoken yet, can you tell me why, if we have something that, like when we think about sines and cosines, right, we think about triangles and we say, well, the sine is something called the opposite divided by the hypotenuse, and the cosine is the adjacent divided by the hypotenuse, right? What does this picture have anything to do with the wave? Why is a wave described by a sine and a cosine? Can anyone who hasn't answered yet take a crack at this? Does anyone know why? Is this an easy concept? Is this familiar to you, to everyone?
Yeah, so if we take the angle along the x-axis and the value of example, if it's a sine wave, the x-axis it just represents the different values of angles, and the y-axis it's the sine of. So if we have one value of θ1, it would have a particular corresponding value of sine. θ2 would have a different value. We just plot it as a graph. It goes on
Okay. So we're taking the values of different theta's, inputting them into a sine, and well, saying that it's a graph, and the graph looks like this, right? But how do you calculate what the sine is? How would you do it? Do you mechanically measure the angle of this thing and the length of this thing and say, well, one divided by the other is precisely this? Does anyone have another answer? Does anyone know what it has to do with circles, for example?
Yeah, okay. So a circle's projection can be, the projection of the wave can be compared to the circle. We can define it. The change in position of the wave, change in position in the wave can be represented as a projection of the circle. For object, okay. So, okay, simple example, consider a ball rotating, we have a thread. So what we do is we rotate it around a fixed point, and that can be represented as sine wave or a cos wave, depends, whatever we can do. I don't know whether I'm getting to the point, but I don't know how to explain it. Maybe I can do it. Take a pic and send it to you.
Sure. Is this trivial? Is this question trivial to anyone? If you've all seen this before, I can move on and not waste time on the digression. But if this is something you haven't thought about before, it's a really beautiful and elegant answer. Have any of you seen this before? Why or what triangles and the sine have to do with the wave?
I think I have come across this before, so I kind of know this.
So what's the answer, Yuvraj?
Okay, so this thing, this whole stuff doesn't have anything to do with triangles, but instead it deals with a circle. So what you do is that by measuring the angle, you measure the motion of a point around the circumference of the circle, and this is actually plotted as theta over here. It could also be plotted in terms of theta, and so if you consider the whole setup to be static, like if you can express this in a normal way, what happens is that it looks like an motion which goes up and down. But when it progresses further, like if you consider this motion along and time interval in kind of thing, what happens is that this time goes on increasing, and therefore this motion it goes on having a curve rather than it being a circle.
Okay. I'm just going to do the quick mathematical explanation for why you can consider this to be a circle. Just hopefully it ties everything in, and we can move on from this to the Lorenz transformations. And the way to see this is if you take the triangle that we have here, and in the triangle, I say I'm going to divide everything by the hypotenuse, right? I'm going to take the opposite divided by the hypotenuse, the adjacent by the hypotenuse. I just get 1 for my hypotenuse, and this changes to cos theta, and this changes to sine theta, right? Everyone sees this. And if I ask what the length is here, by the Pythagorean theorem, we find the usual well-familiar result, that sine square plus cos square is 1. But the argument for why this is a circle is that this is no different from the, if I identify cos and sine to be my x and y coordinates, then if I have a point cos theta and sine theta, this is just the equation x squared plus y squared equals 1 is the equation of a unit circle. Which is to say that if I have my axes here, this point, this point, this point, and this point on a circle, what this tells me is that my distance from the origin in the x direction, whatever this is, which is 1 to start off with, is what I call cos theta. And my distance from the origin in the y-axis, this way, is what I call sine theta. So when I start at this point in the circle, cos theta is just this length here, 1, and sine theta is 0. When I move along the circle, the length from the x-axis shortens, or the length from the y-axis, the opposite way around. The height of this particular thing increases, the distance from the origin decreases, and at this point in time, the height that I have here, which is sine theta, is 1, and cos theta is 0. And that continues. So you guys got it right. You can mathematically treat it as a walk around a circle. And when you plot that out, as one of you said initially, you get that form. And the point I'm trying to make with this is that when you interpret the space-time interval and the length, that's essentially what, when I say space-time interval, you have to immediately think scalar. And just like how if I go around this circle, right, cos theta changes, sine theta changes, what doesn't change is that the length of the circle will always remain 1. Whether you're measuring it this way, it's 1. Whether you're measuring it this way, it's 1. And we have a similar analogy for this. And the analogy is to say that when you look at the equation t squared is equal to x squared plus y squared plus z squared, this is essentially a cone. It's a double cone. And when you plot out what this looks like, in 2 dimensions, it would be a hyperbola. But in higher dimensions, where I've suppressed some of it, it forms a cone. And what I've essentially tried to prove so far is that what doesn't change, regardless of which observer looks like, is that, this thing here. So this is the preserved shape, just like how in the circle, the radius is preserved. And in this shape, we're always going to be preserving the speed of light. And the thing that doesn't change is this thing that we call the space-time interval. Right? Everyone clear? Does everyone understand the first question that I got from everyone last time? Like, where does this minus sign come from? What does it represent? Is that clear now?
Just sorry to interrupt. I'm audible?
Yeah.
So, like your previous question in which you asked about the circle, why we present sine and cos in the form of. So, can't the answer be that because sine and cosine, both functions, are basically a harmonic function, so they will basically represent any kind of harmonic motion.
Yeah, but then the question is, why is it a harmonic function? And how do you interpret that? This was just a picture to explain what that is.
So they are a harmonic function because it's like because the double derivative, because del square of that function will be equal to 0 always.
Yeah. Yeah, so there are different interpretations for how this works. You can even interpret it in terms of complex numbers, but this is one picture that's particularly useful. Okay, so let's now start mathematically with the other stuff that I wanted to get to, which is I want to start now talking about this. Remember, so in relativity, what doesn't change, okay, is what am I showing on my screen? Yeah, can everyone see what we're talking about right now? Okay, no one can see my screen. This is the radius of my vector. Okay, regardless of what observer looks at it, this is the thing that doesn't change. And if you remember, last time we said that if we define the 4 vector, which is just t, x, y, and z, I can represent this thing here by saying that this interval is g mu nu times x mu x nu. Does everyone see this?
Yes.
Yeah, we can see it.
And if you remember, we said that g mu nu was this particular thing. Right? So this is the matrix which represents the transformation, just like how you had, this is the matrix that represents the transformation that leaves this thing invariant. Okay, so there's one particular thing that I want to address here. Some of you may have heard of these things called covariant and contravariant vectors. Has anyone ever been confused about what these are? Has anyone not heard of these terms before?
I have not heard of covariance, but no, I don't know what those are.
Okay, so I just wanted to give you a simple explanation for what this is. And remember at the end of the day, right? So this is the fundamental question that I want to ask you. So if x mu, right, we represent it in terms of a vector, a column vector, right? It's t, x, y, and z. So if this is my vector, or if I give you another example, let's not even take a 4 vector to start with. Let's say I take my position vector and I call it xyz, right? I can't immediately take the length. We know the invariant length of this vector x squared. We represent it like this, right? I can't write it as x, y, and z like this, can I? Because this just forms 2 column matrices and it doesn't essentially lead to, well, a scalar number. And if you remember from matrix multiplication, the only way that we can form a scalar is when we multiply a row vector to a column vector. This is a subtle point. It's often missed in textbooks, but essentially what you need to do to form a scalar, remember we started this by saying we want something that's a scalar. The way that we form this out of 2 vectors is to take a row vector, multiply it by a column vector, and this product, which is x squared plus y squared plus z squared, right? This is a scalar quantity. It's no longer a vector anymore. It's just a number and it's an element of R, right? Does everyone see this? Does everyone agree that if for me to find the vector, the notion of a dot product, it needs a kind of vector, a row vector, and it needs a column vector. Does anyone disagree with what I'm saying right now?
No, we agree with you. We need
So if we need a row and a column vector, right? That's to say that if I have this thing here, and from this, I want to somehow form the quantity t squared minus x squared minus y squared minus z squared, I can't just multiply my position vector into itself, right? Because again, you have 2 column vectors. So the short answer is to say that, well, you need a row vector here, right? You need a row vector. Immediately, you guys can see there's a certain problem with this. Can everyone see the problem if I say this is my invariant length between two intervals? What's the problem with what I've just written down?
We will have a plus sign in between.
Exactly, we have a plus sign. So if I had a row vector, how do I change a row to column? I just take the transpose, right? If I transpose a row vector, I get a column, and it's related this way. Just by transposing and taking one to the other, that's how I move in between a row and a column. But here you can see a problem. If I just directly take the transpose and go this way, well, I'm not going to end up with the same, I'm going to end up with the same vector, which means I'm ending up with something else that isn't my spacetime invariant, because I get a plus sign, which is to say that if I have my column vector is t, x, y, and z, there has to be a minus sign like this. Is this clear? So if I multiply these two out now, we get t squared minus x squared minus y squared minus z squared. Is this clear? So essentially what I've tried to show you here is that while we have two vectors that are the same, we're essentially discussing the same thing, right? One has a minus sign in its spatial components while the other doesn't. So there's some way to distinguish the two. Actually, you could choose, this is a matter of convention. You could say, well, these are pluses and these are going to be minuses. But there's no real difference between the two because it doesn't matter which one's plus, it doesn't matter which one's minus, because the quantity that we're interested in is this one at the end of the day, right? So that's the age-old thing. So essentially what we have is, if we talk about a row vector, we can call that to be x mu. And this particular thing which has the minus signs now, we call that x mu. And we need a way to go between these two, because only if we take these two together, right? Now you can see, if I write it like this, only when I multiply this quantity together will I get a scalar. Because otherwise, if I just take two things like this, I'm just going to get two column vectors multiplied by each other. If I just take a term like this, I'm just going to get two rows. So does everyone see that we need something that's a row and something that's a column in order for me to get a scalar? Is it clear?
Yeah.
It's more like taking a transpose, right?
Sorry?
It's a transpose of the previous.
It's a transpose, but remember, I told you it's not just a transpose, because if I only took a transpose, I wouldn't get this minus sign, right? If I just said, well, x goes to like a row vector, if I just ordinarily took a transpose, we won't get the crucial minus sign that's in my spacetime interval, which means one has to, when you transpose it, you have to give it a minus sign, right? Sorry. Yeah. So if this is the case, remember that when I'm going from row to column, column to row, there's an easy way to represent this, which is the same Minkowski metric that we spoke about earlier. Keep mixing up the pluses and minuses. Yeah, this thing here, if I take it and act on one alone, right? We're going to end up with, let's say this. Does everyone see, like acting on this particular basically when I act on this vector with my transformation matrix, it is the thing which gives me the minus signs in my column matrix. Does anyone see this?
Yes.
Okay,
Yes.
so mathematically, you'll see this in all of your textbooks, and this is what they say when you have, it's called raising and lowering. And in relativity, the language for going from row to column is raising, lowering. So the notation is as follows. So if you wanted to have a row vector, which now in your head you must remember the time component stays the same. One has a minus sign in front of the spatial indices, the other doesn't, right? You can write this as like this, which is essentially just saying for me to have this minus sign, I'm going to multiply it by this matrix in front of it. So if I wanted to say, ask you what the time component is, well, this is 0. Does everyone remember? This was the Einstein summation convention we discussed last time. Anytime you have repeated indices in a diagonal line, whether it's this way or this way, meaning you could even write this way. Anytime you have an index that's repeated up and down, it means it's summed over all of its values. So if I had to write down what x naught is, it's this entire thing. But we know if our matrix vanishes, this is 0, this is 0, this is 0, these terms all go away. And that tells me that time, this is 1. Or if I write it this way. Is this clear? Can everyone see this? Are you happy with this? This essentially is our prescription, what we call in relativity, raising and lowering operators. Which is to say that if at the end of the day we want an invariant quantity, well, the invariant is something that looks like this. If we had a different 4 vector, if it was momentum, it would be this. If you had any other quantity, we'd want this, remember, when you think about it, length. That's what we mean by this. This is the length, but it's a special length because it's a length in Minkowski's case. Is it clear? So now we're looking for all kinds of transformations that we can apply on our space-time vector, 4 vector, which preserve this interval, which preserve this length. Does anyone have any questions before we continue?
Yeah. Okay. So the doubt which I have here is that so this product, the dot product of this vector which you are, the matrix which you are speaking here, right?
Yeah.
So I get it a close similarity between, if you consider the whole matrix to be like the one which I show you now. Like I'll post a pic over here, so which is something which I did over here. And I don't know why, but if you take the conjugate transpose of that vector and multiply it, what we arrive is actually the special vector, the vector that we use to express the space-time. So why is that?
Sorry?
Okay, so the thing is that we generally find out why is that vector has this negative sign over there, right?
Right.
So
why is it a 4 cross 1? I mean, you could just, all those zeros can be thrown out. It's essentially one single column and one single row.
But still, okay, so just for my understanding, I did that. So now, if I take the conjugate transpose of the normal vector that we use to express space-time on all the
conjugate transpose.
Yeah.
Like a complex conjugate and then transpose.
Maybe like considering the time to be a complex stuff. And if you do that and multiply both, and what we arrive is exactly the same that what to say, that del S squared thing actually. Like
if you could write it down and tell me, that makes more sense. I'd just like to finish and go ahead. If there's any other questions with this, we can get back to this at the end of the session.
Okay, fine.
Any conceptual questions with what I've been speaking about? Remember, this invariant length is something that's so important. It's the fundamental equation, because regardless of whether you look at it from upside down on the ceiling, if you're in a car, wherever you are, you end up with this same invariant quantity. It's something that doesn't change regardless of the frame of reference that you look at it from. Okay, we'll get back to the question that you're doing. It's not the transpose, as Bhargava says. Like going from one to the other isn't just the transpose, because there's that minus sign, which means that minus sign alone requires you to do to work with this metric. So I just want to give you a quick rule. So if you remember, what I just told you is that this. So you have 2 rules. Remember, so the reason I asked you if you think about contravariant and covariant is that in literature you might find one of these called the contravariant, I keep forgetting which one is which, and the other is called covariant. That's essentially all we're doing. One represents, like, this is the first approach to it. So as a first approach to relativity, you can consider one to be a column, one to be a row. When you go into this in detail, you'll find more complexities. If for those of you who've studied linear algebra, what I've essentially told you is each vector has associated with it something called a dual vector space. And what this metric does is it pushes one vector to its dual, and it takes the dual to itself. It goes back and forth between the vector space and the dual vector space. That's the mathematical explanation for what the metric does. If you want to go even further into it, it's something called a pushback and a push forward and a pullback metric. But for now, what we're going to say is one's a row vector, one's a column vector. You can't just take the transpose because there's a crucial minus sign, and the minus sign, it contains in it all of the physics of relativity, which means you need some kind of matrix that helps you understand how to go from row to column. So remember, and if you can multiply these two together, when you multiply a row and a column vector together, you get at the end of it a real number, which is our scalar. It's the fundamental scalar. It's called the Lorentz scalar. Okay, that's what we're looking for. And I wanted to tell you something else. And so the only difference between what we're doing right now and general relativity, right, is to say that all of space, if I draw it like this, if I draw this to be my space-time, and let's say there's a huge black hole at the center of it, what we've assumed in special relativity is that wherever we are in this space, wherever we are right now, the way to understand, remember, this tells us a length, and this helps us understand distances. So the thing that helps us understand distances is this thing that we called eta mu nu, which is this thing. I'm going to write it out again. Right? So we've assumed that this eta mu nu applies everywhere, regardless of wherever we go. And that's why it's called a special relativity, because it assumes that wherever you are, this is the unique metric that we call that we work with. And in GR, the only thing that changes is that you stop assuming that wherever you go, the metric is something similar to this thing. And if you have a black hole at the center, here it's not equal to eta mu nu, it's something else. And what this something else is the topic of GR. It tells you that distances between space and time, if you've watched Interstellar, if you're around a black hole, your conception of time changes. That's often due to a gravitational potential, and that distorts how, in your 4 vector, how time and space behave. So that's the topic of general relativity. That's the only difference. It's the same thing that we're doing. We're still going to be talking about the invariant length, but understanding how distances work is different between special relativity, where we work with this one particular metric, and general relativity, where you have any general metric that we call G mu. Okay? Is this clear to everyone? I'd like to wrap up because I think there's one last concept that I want to work with in special relativity before we move on to the calculus variations. Okay, so remember, this invariant is extremely important, and as long as you keep this untouched, okay, all laws of physics are the same. And this is an important requirement because so far when you work through your pendulum mechanics or when you look at quantum mechanics, this is not a condition that we've applied. We've not even spoken about what it means to have we used these terms before, proper length and proper time, which is the time measured by an observer, which, if you remember our space-time diagram, is the time measured at the origin. So the idea is that regardless of what trajectory something else takes, the true conception of how time ticks for that person can only be understood if you attach a clock to the particular observer. And this is something that's missing from a lot of the theories. So this invariant is as important as the laws of thermodynamics, which is to say that if you change this invariant and you end up with something that changes depending on the frame of reference you look at, you've effectively made sure that the speed of light is different for different observers, which is almost like violating the second law of thermodynamics. So it's an extremely important invariant. And all laws in the future, especially what we're going to work with together, we're going to be trying to build some model of the universe which always leaves this invariant untouched. Okay, so let's start with doing that right now. So remember, we said that, yeah, everyone can see my screen now, I think. Everyone see my screen? Yeah, okay. So we said that this delta S, right, is eta mu times x nu, which if you remember, eta mu acting on x mu just gives you x nu. So you can write this equivalently as this. You can even write this as this, right? This is our fundamental equation. I'm going to keep telling you about it again and again because it's that important in all of physics. Can everyone hear me? Am I clear?
Yeah, we can.
Yeah.
We can hear you.
Okay. So the first question we're going to ask is this invariant, if it doesn't change, right? Someone else in, let's say, when I write down a prime on any coordinate system, I mean a new coordinate system. And in your mind, whenever you see this prime, I want you to think about a person hanging upside down from the ceiling or a person going in a car. Okay, that's what I mean by this prime coordinate. How do they see it? This thing better be equal to this, right? And how you can do this is to say that if this thing here equals, right? What I'm going to say is here, if you remember what I told you, a Lorentz transformation at the end of the day is something that acts on my, this is what I said a Lorentz transformation is. So now note the difference. This isn't my raising and lowering metric anymore. This is some matrix. Okay, this is some matrix which leaves this speed of light invariant. And we're going to try and answer what this matrix is. Is this clear and not confusing why you have this law? This is essentially me saying, well,
Yeah.
This is me saying, well, the new coordinate system is nothing but a rotation matrix acting on a vector. So I can write this as x prime, y prime equals that cos theta, sine, minus sine, right? And this is just a rule for how the components change. So just like how x prime would be cos theta plus x plus y sine theta, for example, this new law that I have here tells me, well, x prime naught is equal to, so if I have, remember, this is my u. So if I put this, I have, right? Does everyone see this? Right? So this thing here is essentially 4 equations. It's 4 equations. Each equation that I have tells me what the first one, when mu is 0, it tells me what the time equation is, how the new person perceives time. When mu is 1, it tells me about x, y, and z. Is that clear? So we have 4 equations, and the first of which, if I plug in mu is equal to 0, is this thing here. So everyone understands how I write down my transformation matrix. This is the requirement. This is no different from you saying here, x prime is equal to, well, the first element of your rotation matrix plus the second multiplied by x multiplied by y. Right? It's no different from the rotation matrix. I've just said now it's not just rotations, but it's something in general. Right? Is this clear to everyone? Sorry, I can't hear you. It's unclear. Did someone have a doubt?
I said I'm clear with you.
Can you type out? I don't know if it's
You're
just me,
hearing me?
but
Like,
yeah,
am I
better.
audible? Am I
Yeah,
audible?
better.
Okay.
Purva, I can hear you now if you could type out. Apurva, did you have a question or can we continue?
I think she just wanted to say that she could hear you properly.
Okay.
Yep,
Cool.
you can go on.
If everyone can see the screen now, this is the fun part, and this is the bit that we're going to constrain the equations now. So if everyone can see my screen, right? So I've said that this invariant quantity, whether I look at it from upside down or from the car, right, remains the same as me looking at it when I'm standing, right? So in the standing coordinate system, right, what was del S? Well, del S squared is this thing that I'm writing up here, is that, right? So how do I, but in the transformed case, remember that when I transform, I have to act upon it with this matrix. So this requirement that you see in front of you is the thing that constrains what this matrix looks like. And let me show you why. So del S squared is eta mu nu times x mu x nu. On the left-hand side, right, I have eta mu nu acting on x prime now. Yeah. But since x prime mu, for example, is eta mu rho acting on x rho, I can plug this thing in here, and I know x prime mu is some other variable. So just note that if you're confused by where this rho and sigma came from, they're just any variables. I can call it whatever I like. Given that I'm summing them over, remember the only important index is the top one. If I have a repeated index like this, I can call it whatever I want to call it. It can be anything that I like, alpha, beta, whatever I like. So I'm calling it rho and summing over it. So if you remember, this thing right here just says that it's 0, x0 plus 1, 1, 2. And I think it's important for me to write this out again and again because it's quite confusing the first time if you haven't worked this out yourself. So you guys see this. I've essentially written down this sum here, and this thing alone itself is 4 equations depending on my choice of mu. Okay? So I've got 2 such things because there's an x prime mu and there's an x prime nu. So I've got 2 equations like this, and I'm going to take the second dummy index, it's called, to be sigma. So if I replace these 2 transformed coordinates back in here, I find that eta mu nu, okay, zero. Is this clear? This is my left-hand side, and this is equal to eta mu nu, x mu, x nu. Is it clear to everyone? So what I'm going to do right now is, because these are all summed, remember on the right-hand side, this thing itself is a sum of different, this is our invariant length here. And this is a sum. It's x0 plus x1 plus x2, like that. I could relabel what these indices are, and I'm going to choose to relabel these as G. Let's say it should be an eta. Does everyone see this? All I've done is relabel my index because it's summed over. I can write whatever I want. I've chosen to call mu as rho. I've chosen to call nu as sigma. So what I'm going to do is rewrite the right-hand side of our equation as this. So now look on the left-hand side. If you look at the left-hand side, I've got these 2 things that are the same as the ones at the right-hand side. And remember, these are matrices. This you can think of as a column. This is a column vector. This is, if you remember, something that allows us, you can think of it as something that transposes, but essentially takes a row to a column and a column to a row. This, remember, a column of vectors as well. So the only condition in which these 2 things are equal is when does everyone see this? This equation is probably the second most important equation in order of relativity. With this one equation alone, you can write down all of the Lorentz transformations. It's the defining group. This is the defining equation. Is this clear to everyone?
Yeah.
Okay. What I can do to this is, for now, I want you guys can go home and work this out on your own. But in general, matrices they don't commute. Meaning if I have two matrices, they're not in general equal to, AB, if you remember, isn't equivalent to B. Okay, but it so happens in this case that these two are. The metric of Minkowski time and this Lorentz transformation matrix are, the word for this is abelian, they commute. So what I can do is actually pull this out to this hand side. And if I write out this thing without the indices, so if you remember this is essentially four. Yeah, I can have four values of what rho could be. I can have four values for what sigma can be. And this is why I say this is the most important equation that tells you what the Lorentz group is, because I can write down from this equation all 16 elements of my Lorentz matrix. Okay? What I'm going to do, and you can prove this at home for yourselves, is I'm going to take this to the sun side. And I'm not going to write the indices because everything is summed. Okay, so the matrix form of writing what I just did above is this. And I'm going to ask you guys a question here, and we're almost done with this and can move on to the calculus of variations. Does this look familiar to anyone? Does anyone know what kind of equation this is?
So generally, equations like quadratic are generally equations are expressed in this way, like two where matrices lie over there, which has the variables, and in the middle it has the constant matrix, which actually does express the total magnitude and other stuff.
It's not about the
I
magnitude.
think it's similar to eigen some.
It's not an eigenvector. There are similar concepts. Whenever you think of matrices, you have to be thinking about eigenvectors. But the answer I was looking for is there's something known as a similarity transformation. Okay, and this is just, I hate in mathematics when we have jargon for things that are actually really simple to understand. Okay, and the picture for this is actually really elegant and beautiful. So here's the idea. Also, someone's echoing, I can hear myself.
Jackie's asking this.
I can't hear what she was saying. Pugal, is that your mic? I think there's something wrong with your connection because you're echoing. But if you have a question, please type it out. I just want to quickly tell you what this is. So this equation here, when you see something called a similarity transformation, what it's essentially asking is, remember a matrix of any kind, whenever you see a matrix, again, I'm going to tell you, it represents a transformation, which is me doing something to a vector, changing the alignment. It's some sort of transformation. And if you have a friend that's hanging off the ceiling, okay, and in their hand, they hold a matrix A, meaning they're going to take some quantity to them, and they have a vector, for example, and they're going to apply this to them. They're going to apply some transformation in their own language, hanging upside down from the ceiling. They're going to apply it to some physical quantity. It doesn't have to be a vector. It could be a space-time index. So they're going to take A and they're going to do something to it, right? They're going to do something to a vector here. And you standing on the ground, you're like, hang on, I can't make any sense of what you're telling me because you're in a world that's upside down. So what you call 1, 0 in your coordinate system is definitely not 1, 0 in my coordinate system, right? So he's saying, why don't you come up to the ceiling to where I am, right? And you can see the world from my view. And this equation up here, right, does exactly that. That's what a similarity transformation is. So whenever you see three matrices like this, A, B, C, right, I don't want you to think about them as products in your head anymore. Okay, what I want you to do is think of them as transformations. So for example, if the C is made if I take a pen and I rotate it by 10 degrees, that's what C does. If I take B, it rotates it by 60 degrees. So if it was 10 here, I rotate it a further 60. A takes this thing and rotates it by 30, right? That's what this is. So whenever you see ABC, think of this as C transforms something by 10 degrees, B transforms something by 20 degrees, this transforms something by 60. For example, just a rotation. You take a pen and you're rotating it first by 10, then by 20, then by 60. Okay? So when you see three matrices in a row like this, that's what you're seeing right now. You're seeing one sort of transformation, another transformation, and then a third transformation. And here's the magic, and here's the beauty and the elegance. So when this person says, I'm going to be talking about my metric or a 4 vector here, I'm going to do something to it, right? You say, hang on, what I'm going to do is with this first one, this first matrix that you see here, takes you to standing on the roof. Okay? The second matrix is you applying what he holds in his hand. And the third matrix here takes you back from the ceiling to where you're standing right now. Does everyone follow? That's why it's called a similarity transformation, because it doesn't matter what the specific form of what this is. Okay, actually, I should make a statement here. When I have this thing here, the transpose is actually the inverse. Okay, and what I've done is I've gone to his frame of reference or her frame of reference. I've carried out the operation that he's done on his vector, and then I've come back via the inverse. Okay, and that's exactly what we've done right now. This is, I think, really, really beautiful, and that's the second fundamental equation from special relativity. It tells you that regardless of where you are, when you transform from your frame of reference to the ceiling, Asha, your mic is noisy. I think you should type out. Does everyone see why this is elegant? It's so beautiful. It's telling you that regardless of where you are, whether you're standing here, whether you're in a car, right? What you're going to do is you're going to transform back to this person who's upside down on the ceiling, talk about the world that he's seeing, and then you're going to return back to your car. And that's what this equation up here tells us. It's the defining equation of the Lorenz transformation. And any matrix that you can have that satisfies these conditions here, whatever this value gives you for this is your Lorenz transformation. Is this clear to everyone?
So I have a doubt here.
Sure.
Okay. So like as you told that how this similarity what is it, similarity transformation or something, right? Okay, man. Anyways, like how like this whole thing helps us to find out how this thing actually changes over there and you come back here, right?
Yeah.
What if this thing, the thing in the middle, right? Mu. So what if it is should it be actually a scalar, or it can be something which is variable? Because if it's variable,
I understand your question.
so,
Yeah. So
what thing whatever stuff which is a different thing, what you say? Yeah.
okay. So the important thing to note is that we're starting with the idea of a scalar. So remember, we're demanding from here, where my mouse is right now, we're demanding that we expect to find a scalar. And we're asking what kind of transformation leaves that scalar the way it is. So see here, we started off by saying that S prime squared has to equal S squared. So it's not a question of do we see a vector at the end of it. The starting point is requiring that the length of our spacetime interval is unchanged. S prime equals S. Okay, so we're starting with that notion. What this equation actually tells you is that regardless of where you're standing, and you go from someone who's here to someone upside down on the ceiling, or you're going to someone on the car, and then back to your coordinate, all you're making sure is that they are also in the same Minkowski spacetime.
Okay.
So that's a fundamental, beautiful subtlety, and that's what makes it the equation of special relativity. You're saying, guys, can we agree that we're in Minkowski spacetime? And so one person on the ceiling will say, yes, I'm in Minkowski. And you're saying, let me just check. You go there, via Lorenz transformation, you find out that, yeah, okay, they are in Minkowski, which means that they obey the laws of relativity, which means the del S squared is invariant. And they say, cool, we can discuss physics now because whatever we agree on will be invariant because we agree on this space-time interval. You can transform from your perspective to someone who's in a car and say, are you in Minkowski space-time? They say yes. And you say, okay, we can talk physics. But this picture that we have right now, this equation breaks down when you transform to someone's coordinate system and they're on the edge of a black hole. And you raise the question, well, is your space-time metric, does it look like this? Yeah, you ask, well, is this what you see? And the reply you might get back is no. That's not what I see. The space-time interval that I have, it could be something entirely different. It could look, if you're near a black hole, it looks like this. So if you can see the difference between these two, you can immediately see that these have nice ones and zeros, whereas if you're near a black hole, you get something entirely different. And what this is the subject of GR. Where does it come from? What's this metric like? How does it affect our space-time interval? How does it affect how time ticks? All of this is the subject for a different session. But for now, when we're looking at special relativity, the requirement is that we exclude people near black holes from our discussion. We say, we don't care about you right now. There is a way to define an invariant, but for now, when we're talking about special relativity, all we want is to make sure that this fundamental equation is obeyed.
Okay, fine.
Is everyone clear? Okay, I think I'll address questions at the end because I think we have to rush to the calculus of variations next. And I just want to do one last piece of derivation to explain to you how we constrain matrices, which is to say that if you remember our equation, it was this, right? This is our equation. Just using this, I'll give you an example of how we can try and understand what the Lorentz transformation is. So imagine if I take this equation and I take the determinant on both sides. And I'm going to leave it to you guys as an exercise, okay? That you can find that the determinant of this thing, I'm not going to write it out. You're going to find that the determinant of this is 1. I think it's a stupid exercise. I wouldn't give it to anyone. I'd ask you to use a calculator if you have a matrix. It's mundane that we have to find it in schools. So I'm going to tell you that the determinant of this right-hand side, you can calculate it yourselves, is 1. We're going to use the property of matrices that if I have a product of matrices, the determinant is multiplied individually. Do you see this? So if I have a triple product, I can just take the individual determinants, multiply them together, and I get the same determinant. But we know the middle one is 1. Okay, and the other property I'm going to use is the determinant of the transpose of a matrix is the same as the determinant of the matrix itself, which is to say that the constraining equation that we found so far is that the square of the determinant is 1, which tells us that the determinant of this matrix, whatever it is plus or minus 1. That's actually a very important and powerful criteria, and let me tell you why. It's essentially telling me that if I had a 2 cross 2 matrix, for example, right? If I had A, B, C, D, this equation alone has told us that AD minus BC equals plus or minus 1. So using equations like this is kind of how we're going to find out what this ABCD is. Okay, there are many, many requirements like that. Immediately also, if we require that this thing has a determinant, we can see 2 consequences. The first is that an inverse exists. We can only have a determinant if you can go back and forth via Lorentz transformation, right? The second thing that you see is that from mathematics, the determinant doesn't exist for all matrices, but it only exists for square matrices. And that's actually not a very profound statement, but that's essentially telling us that we have a square matrix, which means the dimensionality of our space does not change when we go back and forth. If we started out with 4 dimensions, we end up with 4 dimensions, which is a 4 cross 4 matrix. Okay, is everyone clear? The final thing I wanted to tell you is that it turns out that the Lorentz transformations in the space of special relativity, Minkowski space, are actually pretty boring to begin with. You have rotations, and you have you moving from your frame of reference to someone who's in a car. And that's just called a boost. It's actually a pretty boring set of transformations. The rotations could be in the xy plane, the yz plane, the zx plane. Your boost could be in the tx plane, the ty, and tz. And there are only 3 and 3 of each. So you actually only have 6 possible set of transformations. Okay? But remember, what I said at the end of the day is that this invariant length is something that remains the same, and that's important because this del S squared, we find that it's greater than 0. If it's greater than 0, it means that 2 regions in space are causally disconnected, like they can't affect each other. If it's 0, it means it's light. It's this 45-degree angle. And if it's less than 0, it means it's inside this light cone, which means only if it's less than 0 can 2 objects talk to each other. So it's important in terms of causality to establish that whatever object you're talking about can influence and affect other objects. And it turns out that every object that has mass has to lie inside this light cone. Any object that's massless lies on the edge of this light cone. And this region of space is causally disconnected. Okay, so remember, that's our takeaway, that in the future, whatever theory that we come up with has to remain, has to ensure that the laws of physics are invariant if we rotate the system, if we go to a car or someone who's moving close to the speed of light and come back to our frame. So that's essentially the prime cusp of special relativity, and we can go into further details later. As of today, what I'd like to do is introduce you to the calculus of variations. Any other questions on this before we start? I'd like to get moving because we're a little short on time. Any questions? No questions? Okay. What we're about to do now is probably one of the most beautiful and powerful tools that we could have in all of physics. And the concepts that we're going to be working with are what's called the calculus of variations. I want to warn you now to say that the first time that I did this derivation, I was quite confused. I didn't know how these steps were done. Many textbooks in this field don't really explain step by step what we're trying to do. So what I'm going to do and tell you is that try to follow along as best as you can. If you don't understand a single step, think about it. Don't just copy directly what I'm writing down, but try to understand what we're trying to say and why we're going from one line to the other. And the last thing I want to leave you with is to say that you're not expected to be fully comfortable with this the first time you see it. But the only way that you can get comfortable with this is by practice. Like, do it again on your own. Try to see and play around. Ask yourself, why is this true? Why isn't that true? And if you do, if you practice these equations again and again, in time, this derivation will become easy to you. Okay? So let's talk about the calculus of variations and why it's probably the most important equation in all of physics. So to start off with, right? If I asked you and I drew a function in a graph like this, right? And I asked you, well, if I have some function, and I asked you to minimize this function. Minimize meaning I'm trying to optimize this function. I don't want to just, if I'm working with a theory, maybe I'd like to work with a theory that takes the shortest possible distance between two paths, meaning that it's a straight line, whatever this function is. Maybe I don't want to have a minima, maybe I don't want to have a maxima. If I'm working with an oscillator, there's a difference between a shape like this and a shape like this, right? So the difference between these two is I'd like to say that at this point, whatever it is, that the second derivative is greater than 0. Here it's less than 0, right? So if I wanted to find a stationary point for an ordinary function, I just take the derivative of this function. And wherever the derivative is equal to 0, that corresponds to points like this, local minima and local maxima. These are all the points on this function that I have, where if you take the derivative and the derivative vanishes. What does it vanish? It means that if I take a small step in this direction or a small step in this direction, the output of the function is actually 0. Function of x plus delta x is 0. So that's essentially what the minimum or the maximum is. It's a stationary point in my curve. And I can find it by just taking the derivative of a function and setting it to 0. And this is what we usually say when we talk about minimizing a function. Right? And it's not really minimizing, because if you take the first derivative and set it to 0, you're only finding an extreme, which is either a minima or a maxima. But we're going to be working with other things in physics which are more general, which are, for example, if we're not working with a line that we know. Okay, but remember I said when you think about space, you draw a diagram like this. And let's say I draw a point A and a point B. Right? Now, this isn't just a line anymore, right? This isn't even a curve, but I'm going to ask you what function, this is important, what function minimizes something between these two, like maybe the distance. What function out of many different functions that I could have? This could be some line that's f of x, this could be g of x, this could be h of x, right? What out of all of these functions, which function minimizes the quantity that we're trying to study? It could be distance. Which function minimizes the distance? And I can give you an example of this sort of problem, which is that if I have let's say I have a slope here, okay, like if I on top of a table, let's talk about this as a table, and I have the ground here. Let's say this is point A and point B, and I connect this with a thread or whatever, and let's say I have a ball that's going to be rolling down this thread. I ask you, what's the shape of this thread that allows me to roll this down in the quickest time possible? And you could say that there are a few easy answers to this. The first answer could be, well, it's a straight line. The second answer could be, well, it's sort of slope like this. It could be even a slope like this. How do I know between all of these different functions? This is a line, whatever that is. Right? Out of all of these functions, which minimizes the time taken to go from here to here? And that's the question that we're asking right now. And this particular problem that I told you is a very famous problem in the calculus of variations. This is called the Brachistochrone problem. It has to do with gravity, and it's a more complicated case of something we're going to be studying today. And in today's case, we're not going to be talking about an external potential, but just a very simple mathematical construction. And if I say I want to minimize the distance between 2 points, how would I do so? Well, we know the distance between 2 points is you can't see that. So let me just write it here. Sorry, one second. Okay, so if I say the distance between 2 points, A and B, I think by now you've gotten bored of me writing the distance formula. Okay, so I'm going to ask what function minimizes the distance between A and B. So I want to minimize this particular thing at the end of it. Just a bit of terminology before we start. Usually, if we talk about a function and trying to minimize this, right, that's called a function. If we have something else, let's say capital F, which is a function of functions, this thing is called a function. And this is the thing that we're trying to minimize. We're not asking you what number at the end of it answers our question. We're asking what function answers the question that we're asking right now. So I'm not asking what line or what number of physical distance is the shortest, but I'm asking how do we know, or how can we prove that the shortest distance between 2 points is a straight line? And that's the question we're trying to ask right now. So if I take this to be the distance, immediately you'll be familiar now. I'm saying, well, I'm going to draw a set of coordinates here. Okay, that's what I'm going to do. I'm going to label it by a set of coordinates. Just draw lines like this. So my x and y. I'm going to say that this point here is at 0, 0. Okay, and if it's at 0, 0, by now you'll know that, well, I can take x1 to be 0 and I can take y1 to be 0. So all I'm trying to do now is minimize the distance between x squared and y squared. Okay, what I'm not going to do is not try to take this as a huge function, but in the spirit of calculus, try and understand small intervals at a time and just go step by step from point A to point B. And the way I do this is I can take my unit of distance, and we call that ds, and I'll take x squared out of this common. Okay, that's my distance at the moment. And what I'm going to do is I'm going to take the limit where we're going to take x going towards 0, or like a very small interval. And we say that the distance then in a small step. So what's the distance between this and this point, for example? Well, it's dx okay. That's our function at the end of the day. And what we're going to try and say is we want to minimize it. So this is just the interval of the distance. It isn't the whole distance. So we want the whole distance from t1 to t2, or x1 to x2, whatever the variables of the integral are, is equal to what is y? Dx 1 plus, I'm going to call this y prime. Okay? And the goal now that we have to do for ourselves is to minimize this. Is everyone clear on the premise, the starting point? We're trying to minimize something, but we can't just take the first derivative and set it to 0 because we don't know what we're finding the derivative of. We're working with something called a functional, which is a function of functions. And the output of such a functional is a function that you're looking for. So you're no longer asking what line best shortens whatever I'm talking about, but you're asking what function at the end of the day gives me the shortest possible distance between two paths. Is this clear to everyone?
Yes.
Okay. So before we go on, something that's important to talk about right now. Remember this. This is our fundamental goal for the end of this talk. Right? We're going to minimize this. But I wanted to say that it's not often just a problem about finding the distance between the 2 points, but rather when I talk about distance, there are many more interesting applications of the concept of distance. And what I want to start by talking about is something in physics that we call phase space. Is this a concept that's familiar to you all before? Has everyone heard of phase space before? Is it new? Did you tell me?
It's new for me.
I think it's new.
Okay, excellent. This is great. It's so much fun. And you'll often find that instead of working in physical space, right, you can often transform and talk about the dynamics of, when I say dynamics, I'm talking about how things move and change with time. It's easier to talk about that, for example, in the space of states. Okay, and what I mean to say is that instead of me physically writing down what the position is and how this ball moves, I can say, well, if I know the ball could be in any one of these possible, let me give you a better example. Instead of me talking about rolling a dice, I can work on a space of states where on my axis I could have 1, 2, 3, 4, all the possible outcomes for me rolling a pair of dice. And if I understand and play around with what this is, maybe I can talk about some truths in the real world. So what phase space is the description of any physical quantity that you're talking about. Well, we're just going to talk about it in a space of all possible states that this could have. So I want to start by a definition and ask a question, and I want answers from some of the people who haven't spoken as yet. Okay, the question that we're going to be talking about is of observables, something that we can observe. Okay, and the question we're going to ask is, what is the minimum? Okay, I'm not going to say minimum because that means integral. Or what is the least amount of information we need about a system in order to do predictions? It's actually a question you should all ask yourselves, because whether it's about a person falling into a black hole, whether it's about you talking about two particles colliding with each other at CERN, right? We don't want to take more information that we have. We have to talk about the least amount of information that's useful to us and then just say, okay, it's enough. I don't need the experimentalists anymore. I can just work with what I have right now, and that's okay. So the question I'm going to ask you right now is, what's the minimum amount of information that I need to be talking about something? And this question that I'm talking about right now changes depending on the kind of physics that you're doing. Okay, and let me give you an example of what these observables are. So if you were doing astrophysics, I think you guys are interested in this. Well, it's no use for me to say, well, what's important to me is, for example, the momentum of something, because that's not an observable that comes easily to you. Given in astrophysics, everything that you do is through the means of telescopes. It makes sense for you to define your observables in terms of light, which is, for example, the kind of frequency that you observe. The kind of frequency that you observe, it could be the luminosity of the light, right? It could be the radial velocity. Another important thing in astrophysics is the temperature, right? These are all important quantities that, once you think about these and say, well, can I get one from the other? Is temperature related to frequency in any way? So can I eliminate this and only talk about frequency? What about luminosity? So these are the questions you ask in astrophysics, right? In thermodynamics, all the information that we have about the system. So why do we even study thermodynamics? Like, I hated thermodynamics when I was studying it in uni. I hated it. I didn't know why I needed to know what an adiabatic transformation is and what the point of all of thermodynamics is. But the reason I came around to it was to say that if I'm trying to model quantum mechanically, even like a gas moving around, like a hydrogen gas, right? Given that you remember from chemistry that 1 mole of a gas has some 6 into 10 to the power 23 atoms, right? Good luck trying to model each and every one of those via the Schrodinger equation. You can't do the Schrodinger equation for this many number of systems. So it just is impossible. The thing to do is talk about group and collective phenomena such as pressure, well, the volume of something, the temperature. Right? These are the observables that you talk about. And if you can understand on a graph how the pressure and the volume and the temperature relate to each other, maybe you can make predictions about what this system looks like. Okay. Now we come to mechanics, which is what we're trying to do today. Before we go to quantum mechanics, this concept applies that we're doing right now. The calculus of variations applies far-reaching consequences to everything from quantum field theory, supersymmetry, particle physics at CERN, quantum mechanics, classical mechanics, wherever you want to do physics. At the end of today, you will have the primary equation that leaves you feeling like you're a god. And that's what we're going to do. So the question I'm going to ask right now is, what do you think are what information do we need about an object under study, right? When we're trying to do mechanics. And by mechanics, it could be, well, what's the stopping force of a car? It could be throwing a ball. Those are all like boring examples. But yeah, these are things that we can talk about. So can anyone who hasn't spoken yet, I think Yuvraj and all have spoken, Apurva, Rachna, Ashmi, all of you, could you tell me about what you think is useful information that we can get of a particular system?
It's velocity.
Okay, velocity. Then?
Mass of the system.
Mass. Anything else? Okay, so I wanted to point out something. This velocity is great, but it's also a derivative of the position, right? So if we have a well-defined function that talks about the position and we had initial and final conditions, surely we'd be able to talk about the velocity as well. So maybe the position is something that's more fundamental to what we're talking about, right? But let's look at other questions of other quantities here, like luminosity, which helps us in astrophysics. Is the luminosity of a car going to help us and predict how long it takes for the car to stop? No, doesn't. We don't care about it, right? What about the temperature? No, don't really care. I don't care what the temperature of a pendulum is. I don't care about pendulums to begin with. What about the third one? What about energy? If we know the energy of a system, perhaps we could do something with it. Right?
Yeah, potential and kinetic energies, but like in Lagrangian, we predict.
So potential energy and kinetic energy, those are the terms thrown around. But when you start to think about it, you find out that energy itself, well, it's defined in terms of velocity, right? The kinetic velocity is half mv squared. So it already has a velocity in here sitting. The potential energy, well, it depends on the form of the potential that you're in. If you're in the gravitational potential, whatever it is, right? So what I'm trying to say is that energy puts us on the right track, but it points us back towards velocity. And interestingly enough, if you consider the momentum of an object, it takes two bits of information that are quite useful. It takes the mass, which is something that we need. It also takes the velocity, and in one quantity expresses that well. Okay, so when we do mechanics, what I'm going to say is that the two fundamental quantities with which we work with our system is the position and the momentum. Which is to say that if I know the position and I know the momentum of my system, I can tell you in 10 seconds what it's going to do. I can tell you what it's going to do in a year. I can tell you what it's going to do in 10 years. As long as my function holds, these two bits of information are all I need to describe the state of my system. And by state, I just mean, well, where is it? How fast is it moving? Which direction is it moving in? Right? Is it near something of importance? All of that is uniquely determined by the position and momentum. So that's our definition. Our definition is that a state, and I'll tell you why I'm writing this down. Guys, just 1 second. I'll be right back. I'm going to take a 2-minute break. I'll just be right back. Hi, can everyone hear me? Okay. Can everyone see the screen?
Yeah.
Okay. So remember, we start by saying that the state of any system is uniquely determined by this position and the momentum. And even me writing down the word uniquely is important. I'm not going to give you a definition with random words. Every single word in this definition is important. So why do I say uniquely? Well, because if you can find a system where two sets of observables, like maybe a different position, 1 and 2, and maybe some other momentum.
See your screen. The screen we can see like your.
Oh yeah, sorry. Better? Yeah, thank you. Okay, so if you happen to have two different vectors, for example, that talk about the same state, you lose this uniquely determined condition. And it turns out even this particular thing is so important, and it's something called a gauge theory. You may have heard of this word in electrodynamics. You find out that the potential which describes the photon is not unique. You can have different potentials for the photon that result in the same universe. And in quantum field theory, this becomes an important condition, that you find out that, for example, neutrinos can oscillate amongst themselves. You find out that the strong force itself is described by something called a gauge theory, and the weak force too is defined by a gauge theory. So all of the fundamental forces in the world that we observe are actually spoken and described by gauge theories. And so the point I'm trying to make is that all of this is built into the mechanics and the dynamics of what I'm trying to talk about. And just when you leave behind the vanilla and standard examples that we talk about, that's when the world gets really interesting. So just like how when you move away from Minkowski space and say, okay, the metric that I'm working with isn't that -1 +++ or plus minus 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 1 anymore, but it's going to turn to be something more complicated. That's general relativity. When you move away from this classical theory, well, you get to real fundamental truths about the world. Okay, so that's something I just thought you might find interesting. But what's true is that if you can understand how the world works with the first and easy basic case, that's how you apply it to the difficult cases and try to understand how the world works. So the state is uniquely determined by the position and the momentum. That's all the information we need to describe a particular state. And what we do is we draw the position and the momentum in something called a phase diagram. Okay, and all that is to say that I take, instead of me having an x and y coordinate, in my x coordinate, I write down the position. And remember, I've suppressed dimensions. When I say position in your head, you want to be thinking x, y, and z, right? And on my y-axis, I have momentum. So I'm going to call that p. It's a momentum vector. These are all three vectors, right? And so now look what happens. If I plot any particular, let's say a point, a particle, a car, whatever is here, and it's moving with a certain velocity, well, I denote it like that. So if I write down all the possible states that I can have, it just looks like something like this. You have order, you have disorder, depending on the constraining equations, just like we saw with the Lorenz transformations, depending on the constraining equations that you have, the system could be complicated, it could be simple to understand, but you guys would have seen, I think Pugal also linked a few images to what vector spaces look like. So that's kind of like if you plot out the various different positions and momentums that you could have, you end up with a space like this. And any point in this space is what we called our state, because any point in this has a unique position and a unique momentum. Right? Is this clear to everyone? So it's useful to talk about the dynamics of motion by looking at this thing that we call a phase diagram. And I want to give you a quick example of one such phase diagram, which would just be a pendulum, because that's easy to understand. And in a pendulum, what happens? Well, we start with a, sorry, I should scroll down. Remind me to scroll if you can't see what I'm doing. Okay. So in a pendulum, we just have something that's hanging here. Okay, some mass, right? And we just say this is 0, L is equal to 0. And let's say it swings to the right to a distance L, swings to the left to a distance minus L. Right? That's what our pendulum is. How do we describe this pendulum in terms of its position and momentum? And I don't want you guys to just write down here, but take a look at the screen and try to understand what kind of quantities you're measuring at. So in this graph here, this particular region talks about a positive position. This sort of a graph talks about a negative position. Here, where your momentum is negative, it means that you're decelerating or accelerating in the opposite direction. And your momentum on this side means you're moving, in that particular direction, right? So if I have this pendulum here, let's say I start at the position L, right? So if I draw my phase diagram, for example, I start, this is my position, remember? So I'm going to write momentum on my y-axis and a position on the x-axis. I start at L, right? What is my pendulum going to do? It's going to move all the way to minus L at some point of time, right? And it's going to carry the same momentum. Let's assume there's no air resistance. What it's going to do is it's going to go from one side to the other, then switch to the opposite momentum, come back, and this process continues indefinitely. So now look, when it's at minus L, right, the momentum carries it towards L. And when it's at L, the momentum carries it towards minus L. So I can draw the phase diagram like this. Does everyone agree? Right? That's how simply like the pendulum looks like. And you can see how this doesn't correlate to the physical way that the pendulum moves, but it helps us understand the motion of this thing by looking at the phase diagram. Right? So that's these two quantities. Like at every point in this diagram, I can go back and say, oh, this point is here. Oh, this point is here. Right? That's what I can do. And what's important is this phase diagram helps us predict where the future is. So for example, if if I now had air resistance, meaning this pendulum is going to slow down when it goes, we can start by saying, well, if I let it go from here, it's going to carry some momentum till p, but slow down. So on my x-axis, on my y-axis, it started out with some momentum, but ended up with something less. You see, but it's still moving towards L. And then when it reaches here, sure, it'll go down. And now when it's on its journey back, let me draw this better. When it's on its journey back, it again loses some momentum to air resistance. So if it started at the point here, it's going to end somewhere here, which is to say momentum maybe looks like that. And now it goes back up. So you can see how an inspiring pendulum that at the end of the day stops, meaning it stops at L equals to 0 here and momentum equals 0. This is my final state. So an initial state here, I can draw a pretty good phase diagram. And at the end of it, it tells me and paints a picture for where this thing is going to go. Why is this important? Because these aren't just points, but remember, this is a vector space. So if I had an arrow of my momentum here pointing here, I know that any pendulum that starts off here is going to be kicked in this direction. And if there's like another momentum vector here, it means it's going to be kicked downwards. So knowing how this phase diagram looks, often with looking at it, I can tell the direction at which it's going to go next. I hope this was a good example to everyone that came across is clear, and you understand why phase space is something that's useful to think about and why we're talking about observables in the first place. Right? Is this clear? So now I want to go back to our problem here. Right? Our problem at hand, we're going to call it I. And we're going to say that this function I, remember, we're not talking about a real number anymore, but we're asking for what function between 2 points, right? And if you remember our observable in classical mechanics, well, I said it's position and it's momentum, which is related to, it's related to the time derivative, right? It's related to the time derivative of this vector. We know that whatever we're talking about right now, position itself changes with time and the velocity itself changes with time. So our function at the end of the day is going to be some function of time, some function of position, and some function of momentum. Right? And the goal at the end of the day is to minimize it. And why are we trying to minimize it? The principal axiom of all of classical mechanics says that if you have 2 paths from A to B, but not anymore in physical, physical space, but in phase space meaning position and momentum, right? The distance between these 2 points in phase space is such that it's minimized and it takes the path of least resistance. And this principle is something called the principle of least action. And this is so important because if you understand this and understand how to work with this, you can derive Newton's laws. And at the end of this, we're going to do that. You can derive that the shortest path between 2 lines is a straight line. You can derive fundamentally how, for example, the fundamental law of nature for photons, the electromagnetic field, the quantized, the Higgs field, for example, as well. Everything, every particular field of importance, you can understand the equations of motion through the principle of least action. And that's a very, very important, I'd say it's the most fundamental equation in all of physics, which is why I'm shocked that you don't learn it in your undergraduate. It should be the first thing that you learn. Okay, so it says that whenever you go from point A to B, and you could do so in many different ways, the path that takes you from A to B has to be minimized. And this is called the principle of least action. And we're going to understand the consequences and what I'm talking about. So does everyone follow why we've chosen these 3 observables? So this is a choice. I've chosen that the function that I'm talking about right now talks about position, talks about momentum, and has time. We don't know what this function is. It could be any function of time, position, and momentum. What do I mean by that? Here's an example. I could say, well, it's x squared plus p cubed. And I say, for a particle moving, this will always be minimized. And you'll say, what? Is that true? Why is that true? So the point is that it helps us constrain what possible functions a position any particle moving from state A to state B, no longer points, but state A to state B is. Is everyone clear on this?
Yeah.
Okay, so when we choose with our general function, right? Remember earlier when I spoke to you about what this function could look like. Remember we formulated this problem as a distance between 2 points. We've now understood what phase space is and reformulated the problem as a function of time, position, and momentum, right? This particular choice of these three observables is so important that it's given its own name. So this functional, and when I say functional, I mean function of a function, meaning f of t, x of t, and dx by dt of t. If I solve what this is, my answer isn't a number, but it's some function, right? This functional is so important. The name given to it, can anyone guess?
Lagrangian, yeah.
Okay. So what our fundamental principle of physics? That's how important this is, and I really am shocked you don't learn this. Is that whenever we go from one position momentum state to another, the path that this particle takes is such that the action is minimized. And the function that does this is known as the Lagrangian. Okay, so our goal right now is to minimize this function at the end of the day. Okay, now here's a bit. So the following, this is where the derivation of the Euler-Lagrange equations and everything starts. And I'm going to do my best to walk you through it step by step. But at the same time, I was thinking about it. Like I could deliver this topic with maybe 5 minutes of prep time and show you the mathematics like fairly quickly. Or I could take you through the full bells and whistles and show you the entire rigor. So at the end of it, it's like waterproof. There's no possible holes in the proof. And I thought it might be a little more challenging to follow, but I'm confident that all of you will understand. And if you practice this at home, you can do it without looking fairly easily. Okay, so here's what we're going to do. We're going to start by saying that we have in phase space, right? And we're going to take a point. Remember, it's a function of time. So we have 2 points, t1 and t2. And we're going to start by assuming that we have some function that takes us between t1 and t2. Okay, we're going to call this the original function. And the way we minimize it, okay, is by adding a small amount of disturbance or noise or like a variation to this function that looks like this. And we're going to ask the question, right? What constraints can we do between these two that help us minimize and figure out which function between points t1 and t2 is the minimum, is the thing that minimizes this thing on the left. Does everyone understand? So the starting point that we're going to do is we're going to claim, the starting equation is that we're going to claim that this original function, right, minimizes the action. So it's like this. If I were to, let's go back to talking about functions, not functionals to begin with. If I was going to say that, well, the derivative of this is 0, I've started by assuming I have a function and I asked, where is this a minimum at? And then I get the, well, whatever value of x such that the derivative of x is 0. Right? That's the question I've essentially asked. I've asked you, what values of x result in the derivative of this being 0? And if you can tell me what values of x result in the derivative being 0, those correspond to the maxima and the minima of my graph, right? I'm going to do the equivalent thing, and I'm going to say, well, df by dx is 0. Okay, what value of x lets me do this? So that's essentially the starting point. We're going to start by saying that this original function minimizes this action. And I'm going to ask you, like, what changes to this function in terms of this new function minimize this? Or what conditions must this function satisfy such that this original function that we have here between 2 points in our phase space is a minimum? Okay? So the first key point that I want you to think about right now is, again, I'm going to say this multiple times. This is a function of a function. This is a function. Right? So immediately, what I want you to be thinking about is that if I were to ask you, so here, if this was any curve x or y that went between 2 points in my xy plane, right? I can add a number to my curve y. So for example, if I take y is some mx plus 5, right? That's how I change my curve, by adding things to it. I can add 6, I can add something else to it. But here, because it's a functional, right? To my original function, I'm going to add a new function. Is this clear to everyone? It's no longer just a constant. It can't be the number 5. It can't be a number a. It has to be some function whose form we don't know. Is this clear? That's the reason that we call this calculus of variations, because we're working to find the function that satisfies our conditions and our demands. It's not like regular calculus, because in regular calculus, we know what the function is, and we're just asking questions of where is the local maxima, where's the local minima. Whereas here, we're asking questions of what function like minimizes me going from point A to point B. Right? So instead of me adding a constant right now, I need to be adding a function. So I'm going to write down some key important tools here to begin with. So my original function, right, is a function of position. Is it clear? We've made this assumption clear in our Lagrangian. We've said that whatever it is has to contain a function of position and of momentum. So how does this change? Well, I say x of t goes to x of t plus some number times the variation. And I'm going to do this step by step so that everyone understands. This first step is no different from me saying, oh, instead of a new function, I'm going to say f of x goes to f of x plus g of x. Whereas earlier I could say y prime is equal to y plus 5. I can't do that anymore because it has to be some function of y. So I'm going to say it's like this. Is this clear to everyone? What I've done, this first point is the starting of our proof. This is supremely important. Is this clear? So I'm going to pictorially explain to you what I've done here. So this original function, I'm going to redo it in red, right? This is our original function. All I've said is that at every point, like here, between these two things, I'm going to kick it in this direction. And the kick, this interval between the two is s. If everyone can see, that's what s is. Like it could be large, it could be small, right? This distance between these two is s, but what can s be proportional to? S can't be proportional to x. S has to be proportional to a function. Why? Because if I move in this direction, right, this new line isn't a line anymore, it's a function. Every curve on my space here is a different function. This is f of x, this is g of x, this is h of x. Is this clear to everyone? So do you understand why I've written this? I've said, well, my new function is the old function plus a kick times I'm describing it as a function. Is this clear? If you understand this one thing, you've won the battle. Like that's probably the hardest first step. And if you understand this, and even if there's any shred of doubt, tell me. Okay, it's important for you to understand where we're going with this. Okay, so what do we call this? So this is where physicists have a dilemma, and I'm asking you guys to help me. So this new thing, what can I call it? I can call it y of t, but that doesn't help me because it makes it seem like it's a different variable, right? I can call it x prime of t, but that doesn't help me because in calculus, we denote the derivative as f prime, right? So I need some notation for this. And the common notation in mathematics is to give it a hat, right? So it's no different from me saying I'm going from x to x prime, old coordinates, new coordinates. I'm just saying my new line here, this is my new function. Think about it here. Just look at the picture if you're ever in doubt. My new function is my old function plus some kind of kick times a function. This is me just saying y prime is equal to y plus 5. That's all I've done. Is this clear? Okay. Now, a bit of notation. So wherever we talk about derivatives, right, I'm going to soon get really tired of writing df by dt. I'm going to get real tired of writing df by dx, just like how in our special relativity course, I told you I'm pretty soon going to be tired of writing t minus x, y, and z, and I'm just going to replace it by x mu, x nu, right? Writing this is shorthand for something bigger, and I'm lazy. I don't want to keep writing that again and again. So what I'm going to do is anytime I see a time derivative, right, I'm just going to denote that by a dot over it. Is it clear? Have you all seen this before? This is common notation. Like it's used to differentiate between space and time variables. Like if you take,
Yes.
Yeah.
cool. So this is the dot. And so now the next thing I can tell you is if we go back and look at our Lagrangian, not only does it have an x, right, but it also has an x dot, which is how we define the momentum, right? Which is to say that this new function that we're trying to minimize, not only must it have this thing, we're looking for a new function, which is x hat dot. Is it clear? And I want you to now, before I write down the next thing, can someone guess what this would be? All I'm doing is taking the function that I have here, and I'm differentiating it with respect to time. Can someone tell me what you expect me to write on the right-hand side? Just mechanical differentiation with respect to time. Anyone? I don't mind right now.
dxt by dt.
Sorry?
Find dxt by dt.
dxt by dt, okay. Which I'm going to write x dot.
Okay. Plus this s into double dot of del st.
Perfect. Is everyone clear with this step? All I've done is use the linearity of the differential. And I've said that, well, if I'm differentiating this with respect to time, well, I first differentiate the first one plus the second one. This is a constant. So it just stays the same. So this is equivalent to me saying x plus 5, no, let me give an example. Y plus 5y goes to dy by dt plus 5 times dy by dt. Right? That's all we've done so far. Is this clear? So remember, dot is just the derivative with respect to time. So what I've written down, right? So this is my new position and my new momentum. Just you can think about it like that. But what I've done is I've changed my quantities, whatever I call x hat, which is my new function in this graph. I've just written it in terms of the old one plus a small kick. And I've just taken the derivative, the first derivative of this, because we're going to need it soon. Okay? We're almost there. We're almost there. So now I'm just going to show you the next bit of trick that's important. And that's the biggest conceptual problem that's over. Like, and then all that's left is just a little bit of mechanical crunching and we arrive at our final answer. The third statement, okay, is what I'm gonna ask you to do is look at this graph here. And remember this s is the distance between my original function and my new function, right? I'm gonna ask you something. What happens when s equals 0? You can even look at it here. What happens when s equals 0?
Both your position and momentum remain the same. That means the original function was
I can't hear you. I'm so sorry.
Your position and momentum remain the same, and that your original function is like the minimum path of least action.
Okay, perfect. So what he said is that when s goes to 0, okay, what happens is if you look at the equation number 1 here, right? X hat just equals x. Does everyone see this? Because if s is 0, this term on the right-hand side just goes, it vanishes. And my new function is equal to my old function, meaning on this graph here, when s is equal to 0, the function follows the original path. Is this clear to everyone? S is equal to 0 implies x hat of t equals x of t. It also implies x hat dot of t equals x dot of t. All I've done is substitute into these two equations s going to 0. Is it clear? Fairly easy to see, right? And also note, what he said that's important is that my original function, by our claim, is the minimum. Is the minimum. So our question that we're asking for when is our Lagrangian minimized? When is our function, the distance between 2 points minimized? It's minimized when s equals to 0. This is the minimizing condition. Okay, everyone clear on this? The last bit that we have to write is using our initial conditions. And what we can see so far when we look at our new function and the old function is that if you look at the endpoints, since they're the same endpoints, there's actually no difference between here. As we get closer and closer to t1, s gets smaller and smaller, right? Like at this point here, there's no difference between my new function and the old function, which is to say that at the endpoints of my functions, they're the same. And the way I write this is this my kick. Remember, my kick in the function is called delta x, right? At t1, and delta x at t2 equals 0. Is everyone happy with this? This is all that's there to it. There's no more conceptual trickery. All the biggest arguments that we've made so far in physics have finished here. We've started by saying we have a new function that's described by the old function in a kick. We've said we can just differentiate it once and keep it aside because we're going to need it soon. The third thing is to say that our original function is what is the thing that minimizes what we're looking for. And that's true when s goes to 0, right? And we've lastly said that the initial conditions tell us that because the endpoints are fixed, the new function equals the old function at the endpoints, which is my kick goes to 0, right? Is everyone clear on this?
Yeah.
So our step in deriving the equation of the gods, as I like to call it, like really it's the most fundamental equation, is to take our old Lagrangian, right, which depends on time, it depends on position, and it depends on, remember now, this is my momentum, and I've just written it in terms of just the derivative.
Sorry to interrupt. I have one this doubt.
Sure.
Basically, what this kick function physically mean? Like how you physically interpret this kick function? What you have been talking about?
What is this kick? This kick is just, remember, like, the definition of everything that we're talking about isn't physical space right now. It could be physical space, but we've not chosen for it to be physical space. This kick just tells us, if you go back to phase space, right? What I'm essentially asking is, if I'm going from point 1 in my phase space to point 2 in my phase space, I'm trying to go from one point to the other such that this functional is minimized. Meaning it spits out as the answer some function that minimizes, for example, the distance between 2 points.
So is kick function is something like a function which differentiate from my older function to newer function?
It differentiates the old and the new function, exactly, yeah. So if you look at this new function, I have s, right? But if I write my new function, look where my mouse is right now. If I write my new function, it isn't just a variable, but it's a function itself. And because it's close to what my original function is, I'm just going to say it's a variation in that function. Remember, so I'm just varying whatever this line is, and because I'm varying the line to say I'm changing it, whatever this variation is has to be a function itself. Which is why when I say it's a kick, what I'm trying to say is that I'm going to kick it by a various amount via s, but the kick itself is represented by this delta x. Is that clear?
So this kick function will be again the function of the same momentum and time as well as space.
It's just position as of now. It's position. It's some functional position. It could be x squared, x cubed, x to the power 4, okay, whatever.
So it will not include momentum and time parameter.
No, it is a function of time, because the entire phase space that I've spoken about here is a function of time. So it's to say, for example, like let's say my original function is x cubed. When I'm kicking it, my new function could be x to the power 4. For example, and then we've also defined on this what x dot is. All I've just said is this kick is a new function, and we're going to try and find out what this new function is, but all we know about it is that at the endpoints, they're the same function. Remember, the point I was trying to tell you, so if you look at here, maybe this explains what this kick is. The kick is just g of x.
Nice. Yeah, I got it.
Okay, so now we get to the starting point, which is to say my Lagrangian, which I defined at point in my old function, right? Everyone sees and agrees that this is what my function is. It's a function of t, position, and momentum. And what it's going to do is it's going to change to L hat, I'm going to call it, which is a function of t that remains the same, x hat, and x hat dot. Okay? Does everyone agree with what I've written? And what this is this is the description of my old function, and this is the description of my new function. That's all that we've done here. Everyone clear?
Yes.
Okay, so now writing out our action, what we've said is I, let me call it I hat, which is the integral from t1 to t2, okay, which is my Lagrangian of t, x of t, x dot of t. Our goal now is to minimize this. Everyone clear? We've just reformulated the problem that we had, and now we've written it concretely. And this should actually be hat, sorry. Yeah, is everyone clear on what I've done so far? Okay, so how do we minimize this thing here?
Yep.
I'm going to say that my functional I, okay, when I vary it with respect to s, when I take the derivative with respect to s, when this is 0, that's the condition we spoke about earlier, is the condition for our minima. Everyone clear? So what I'm going to do now is apply what's called the Leibniz rule under the integral. So what I'm going to do is try and find a way. And so remember, I'm going to be really lazy. Okay, and I'm going to denote anytime I write this, I'm going to rewrite this as this.
I have one small doubt in this.
Sure.
Yeah, so like our condition to minimize the function I or I hat is that its derivative should be equal to 0. But then its meaning is such that it's either of these extremums. So we could also end up maximizing the function, right?
Yeah, we can. So the principle is the principle of extremum action, not the minimal action. So that's mathematical terminology right now. It's either a maxima or a minima. We're looking for an extremum point.
Yeah. But then, like, what if I want to minimize that function, especially?
You look for the second derivative, but that comes later. I'll explain to you later why that's not necessary in most cases. For all intents and purposes, the law isn't to find the minimum. The law works equally well if you just find an extremum itself. Okay, so remember, this is a functional. The case is when s goes to 0, or the derivative of this I hat with respect to s is 0. And how do I do this? Well, we use the Leibniz rule, which is I'm going to do a derivative within the integral sign. And let me just write that out for you. Can everyone see? Okay, so this is the quantity that we now want to take. And how do we do this? Has anyone seen this before? It's actually a pretty cool mathematical trick. We're taking a partial derivative within the integral sign. And the way we do this is something called the Leibniz. Leibniz is a genius, and he's the one who's told us how to do it. And the way that we do this for any function, remember, we don't know what this Lagrangian is. If we knew what it is, then we wouldn't be doing all of this. Right now, we're trying to make the most general case and answer questions and how this goes from there. So if I take the derivative, and I'm going to do it with s, and remember when I write this out, I just mean d by ds. Okay, that's what it means. I'm just being lazy and I'm writing it like this. Okay, so if I take the derivative of some function x and y, okay, you just apply this with a product rule. And how you write this out is you take this to be the derivative with respect to x. And forgive me, but I'm going to write it out as shorthand. Tell me if this is unfamiliar to you or uncomfortable, but this is the way that is the easiest, and we're all lazy. Okay, so I'm going to, the rule for this, the rule for okay, let me write it out here. Okay, this is going to be partial. The rule for this is written as follows. It could be with respect to time. I can write that to not confuse you. Okay, the rule is as follows. D by dt of some function of x and y is you take the first input into the function. Okay, write the function. This. Is everyone clear on what this is? All I've done is written out and told you a rule for finding the derivative of a function. And what I've done is I've taken the partial derivative of the first input into the function, of the function itself, and then essentially use the chain rule here. And I've done the same thing on this hand side. Right? This is the Leibniz rule. If you're uncomfortable with this, send me a message after, and we can go into why that's true and resources for you to understand. But this is the rule that we're going to be using here. So can everyone see? It's the same thing here. We're just going to replace f of xy with the Lagrangian, which now has x dot, and t. And instead of the derivative with respect to time, we're taking the derivative with respect to s. Okay, so let's write it out here. So the first input into this function, t, does not depend on s. It does not depend on s at all. So you can throw that out. Okay, it doesn't matter. The two terms that matter are these. And how do they play a role here? Well, the first thing we get, let me write that out, is integral t1 to t2, right? I'm going to take the derivative of L with respect to x hat. That's important. That's the first thing. That's where this comes in. Times del hat by del s plus dot by del s. Is everyone clear on what this is?
Yeah,
Is this an unfamiliar operation? All I've done is I've taken this Leibniz rule and I've just blindly applied it. I blindly applied it to say that if I have a function and I have another derivative, I do it by taking the derivative of the function with respect to its first argument and then apply the chain rule. Then take the derivative of the function with respect to the second argument and then apply the chain rule again, which is all I've done here. The first term is the first argument, the second term is the second argument, and I've applied the chain rule to find the derivative of the hats with respect to s. Clear? So let's now try to simplify these terms, and we see we can actually simplify this in this way. So if you remember, right, I told you to write this out earlier. X hat is just x of t plus s times del x of t, right? So what is this term here? Well, this goes to 0, and all that you're left with, yeah, does everyone agree? This term goes to 0. The derivative of s with respect to s is 1. You get this. What about this? Well, this thing is just x dot of t plus s del x dot of t. Well, the derivative of this with respect to s is just, this goes out of the window, s becomes 1, we're just left with del x dot of t. Right? So we can actually input that here. So our integral that we had now becomes an integral of t1 to t2 dou L by dou x hat times del x of t plus dou L by dou x hat dot dou x dot of t. And this entire thing dt. Is this clear to everyone?
Yes.
yeah.
Pretty simple. We're almost there. We're about 3 lines away from final equation. And what we're going to do is we find that this particular thing here, the second term, we can integrate by parts. We can integrate by parts because the denominator here itself has a partial with respect to time, and we're integrating with respect to time, so we can integrate the second term by parts. So let's do that. We're going to start by taking this term aside. Yeah, you guys can see? Okay, we're going to integrate by parts. And if you remember the rule for parts, it's saying that if you had the integral of u dv, we're going to write this as uv minus integral v du. Right? And the term that we want to be applying this rule to is dou L by dou x hat dot and dou x dot of t. Is it clear to everyone? We're going to be integrating this thing first from t1 to t2. So what is our function u and what is our function v? I think everyone would have written this in school or wherever you're familiar with under different notation. I've learned it as u dv and all of that. I think you might have heard of it in some other way. So what I'm going to do is I'm going to treat u to be this. Okay. So du, when I take this, we're just, can you guys hear me?
Yeah.
Yeah.
Okay, all I've done so far is taken u to be this thing, and I've differentiated it with respect to time. Okay, and what I'm going to do is choose my dv to be equal to this. And if I integrate dv, well, this is just a time integral. It's a derivative with respect to time which means it vanishes, and the integral of this thing means that v is just dou x of t. Is everyone clear?
Yeah.
Super simple. Super simple, super simple. That's all we need. So now we're just going to take this and apply it to our integral by parts. And our full equation looks like this for now. It says it's the integral between t1 to t2. Okay, del x by dou x hat times the kick function. Okay, plus what we just did by parts. So we take u that's here and we take v. Okay, which is dou L by dou x. Oh no, it's like our uv minus integral dt. Yeah, it's this times yeah. Is everyone happy with what I've written down? This is evaluated from t1 to t2 plus this term here. This term here becomes t1 to t2 minus, we get a time derivative times, sorry. Okay, is everyone happy with this? All I've done is I've taken the second term in our integral here. I've done it by parts. Okay, and by doing it into parts, I've split it into two. The first one is here, the second one is here. Right? Is everyone clear? This bit is the uv, and this bit is the vdu, integral vdu. Is this clear to everyone? Does anyone have a doubt in this?
No.
No.
Sorry, does anyone have a doubt? All I've done is I've taken the second function, I've done it by parts. And because I've done it by parts, I've got 3 terms now in my equation. From 2, it's become 3. But now note here, right? What I'm going to do here, pay attention to this one. What happens is we've got the derivative of our Lagrangian with respect to x hat, right? But we're going to evaluate it between t1 and t2. And if we go back to the third fundamental fact that we worked with here, well, we find that because of the boundary conditions, if you look at where my mouse is right now, this kick function vanishes at t1 and t2, right? So this thing goes to 0. Is this clear? Because this essentially is this kick function at t2, kick function at t1, which are both 0. So this entire term vanishes from our integral. And all that's left is I can pull this under the integration sign there. And I've said all I've got right now is the integral from t1 to t2, dou L by dou x hat times del x of t minus d by dt of dou L by dou x hat times dx of t dt. This should actually be here. Is everyone happy with this? I can even, because there's the kick function in common, I can take that common and write it as t1 to t2 integral. I'm going to write that here, dou x of t. So dou L by dou x hat minus d by dt of dou L by dou x dot hat of dt. Right? Is everyone happy with this so far? We just have one line left. And remember the line that's left. We're saying 2 things. The first argument is that our new function, x hat, is minimized when s goes to 0. Right? And when does that happen? When s goes to 0, x hat just becomes x hat dot also just becomes x dot, which means when I take s going to 0, my integral becomes dou L by x dot dt. Right? And now the final step is I want to go back and use the left-hand side. We had earlier said that the derivative with respect to this of my new function is minimized when this thing is 0. which means what we've written down at the end, right? This thing has to equal 0. And when can this equal 0? It can equal 0 when dt is 0, but that's not useful. It can equal 0 when the kick function is 0, but that's not useful as well because we want to have dynamics. So the only case in which it's 0 is when this middle term equals 0. And we're going to just write that up once. So the partial derivative of the Lagrangian with respect to x minus the first derivative in time of the Lagrangian with respect to x dot equals 0. And this that you have here is the fundamental equation of all of physics. It's called the Euler-Lagrange equation, which tells us that if we can write down a Lagrangian of any form, right, this particular thing gives us the equations of motion. And today, what I'm going to do to end this lecture is give you a few quick examples of what Lagrangians are and what equations of motion this could be. But before that, let's start with the example that we started with at the top of the page, which was, we said I wanted to minimize my distance function. And if I take my Lagrangian to be equal to the square root of 1 plus y prime squared, right? This is my Lagrangian. If we do this, let's say my prime for the y is dy by dx. Okay, and here there's no concept of time. Here it's actually a derivative with respect to x. Okay, so let me just plug this into my equation above here. So this equation that you see in front of you, which was my distance function between 2 points, is there, what if this is L, just do it term by term. What is dou L by dou x? Well, if I differentiate this with respect to, sorry, I've written down the equation differently. Okay, so what's important to know is that when you formulated your problem, this equation is the fundamental one. Okay, you might want to spend 2 minutes before jumping into a problem like I did, just to understand what the x's are, what the t's are, because if you remember, we spoke about phase space. So I made a mistake of just jumping in and assuming that that's what dx and dt is. But what you can do is, if my distance is square root of 1 plus y prime, let's say y is a function of x, and this is my distance. And let's say this is my Lagrangian. Let's find the equations of motion. Okay, so do I have any x dots in this? I'm going to change the equations, but you'll see first. So if I write down what, I get a 0. Okay, if I find the derivative of this Lagrangian with respect to x, what happens? Well, now I have to, okay, so I have to find this. Okay, I have to find what this is. And because there's a square root, we first have to do 1 over 2 root blah, 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 blah. Okay, times, you apply the product rule inside, and I get y double prime of x. Is everyone happy with that? I don't care what this is. I just, if I apply the product rule, if I have 1 over 2 times the square root of something times a numerator, which when I apply the chain rule, I have to differentiate this a second time. And I know the left-hand side of my equation from this is 0. So I've found that I've got some numerator, which looks like this, divided by some denominator, which looks like 2 over square root blah, 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 equals 0. And the only condition in which this can equal 0 is when my numerator equals 0. So from this, the condition that we get is that my distance between 2 points is minimized when y double prime is 0. And this actually is a pretty good result, because if I integrate this once, right? What quantity, if I take the derivative of it, gives me 0. Well, it's a constant. Well, if I take the derivative of 5 with respect to x, I get 0, right? So y prime has to equal some constant. Okay, now let me actually call that constant m. And if I now differentiate, if I integrate this again one more time, I find that y will equal to mx plus c, which is a great result. It's told us that if we have the form of our Lagrangian, the equations of motion have told us that the particular functional that minimizes the distance between 2 points is in fact a straight line. So I think that's a pretty cool result. You can now prove that, and it's as simple now that you've done the derivation of what the Euler-Lagrange equations are. You can blindly just understand what your Lagrangian is, and then if you put it into there, you get cool equations. So let's just do one last example of this, and I'm going to tell you that the way that we formulate Lagrangians in classical mechanics is that it's defined as the kinetic energy minus the potential energy. Okay, and let's talk about the simplest possible case, right? How can you determine what the kinetic energy is? Can anyone give me the, well, you know it's half mv squared, right? But V itself, let's be quick, is x dot. Right? Everyone's happy with that? And I don't know what a potential is. So I'm just going to call my potential V of x. Okay? So now I'm going to take this and I'm going to plug it in to the Euler-Lagrange equations. So from here, right, what is dou L by dou x? If this is my L. If I differentiate this with respect to x, what happens to my first term? It goes to 0 because there's no x dependence here. There's only x dot. It's dx over dt. Whereas my second term, this doesn't become 0. I just get dv of x by dx. Okay, that's my answer. I'm not interested in anything more. That's my answer. And then it tells me the second thing I need to find is the derivative of my Lagrangian with respect to x dot. And what is that? Well, it's half m x dot squared, and this comes down, and I just have mx dot. Right? Everyone clear with that? It's just the derivative of x squared just becomes 2x. So this just is mx dot. But our equations tell us that it's not just enough to take the derivative of our Lagrangian once. You have to take this and differentiate it with respect to time. So the time derivative of this thing is what we're interested in. And what is that? Well, it's d by dt of m times dx over dt, right? Which is m times d square x over dt squared, which is m times a. And now if I write out what our two results is, this is the first one, and this is the second one. If I write this out in the form that the Euler-Lagrange equations have told us, well, it just says that dv over dx, whatever that is, okay, minus m times the acceleration equals 0. And in physics, what we do is we say anytime you have a potential and that potential changes, we call this the force. Which means what we've derived from the Euler-Lagrange equations is force minus ma equals 0, or a physical entity. And that to me is the beauty of the Euler-Lagrange equations in the calculus of radiation. That from starting with first principles, you end up with Newton's equation as the simplest possible example of what a Lagrangian is. So I think that's the end of the talk today. And what I'm going to tell you in the future is, I want you to go home and think about a few things. I'll post a few exercises that you can do. But the question that we want to be asking ourselves from the first part of our lecture to the second part of the lecture is, hang on, our Lagrangian that we spoke about, right? What happens if we act upon it with our Lorentz transformation? Because we spoke about this being invariant earlier. And if we want our physics to be invariant, we should say that L prime under this transformation better equal L itself. And the point I was trying to make today is that the reason that it spits out Newtonian Newton's laws is a consequence, a fundamental consequence of what we just studied, tells you that it's not true. We don't actually get that right now. This Lagrangian that we've done at the end of today, the simplest possible one, right, in fact, isn't a Lorentz invariant, which means it doesn't truly describe physics. And this should not come as a surprise to you because you do know that Newton's laws break down, which is why we needed relativity in the first place, which is to say that in the future, the questions you want to be asking yourself is whenever we talk about a Lagrangian, right, it shouldn't just be a function of t and x like that. Instead, it should be a function of our 4 vector. And it should also be a function of maybe the derivative of the 4 vector itself, and maybe that could be the momentum for vector. And if we have such a Lagrangian that depends on this, well, then if you have the Lorentz transformation acting on this vector, the Lagrangian, it turns out to be equal. And this study is something that's so fundamental to physics that there aren't that many Lagrangians that are Lorentz invariant. Like, it's very difficult to find one that truly describes all of physics. So they're so specific that the fundamental Lagrangians, you could probably write down 5 or 6. There's one which describes the classical electromagnetic force, which is Lorentz invariant. The second is that from general relativity, when you speak about a black hole, you can ask, well, does a black hole have a Lagrangian? Yes, it does. And it's actually called the Einstein Hilbert's everywhere Lagrangian. And then when you talk about QFTs, quantum field theories, you have a whole different set of Lagrangians. And then even further, you can start by asking, what happens if I do quantum mechanics, not in a relativistic framework with eta mu nu, but work away from this near a black hole where you replace it with something more general. If you do these two together, okay, that's quantum gravity. Quantum gravity is nothing other than trying to do quantum mechanics on a non-Minkowski space. So I think that's the end of my talk today, that all of the stuff that you do, whether it's pendulum mechanics, trying to learn Gauss's law or various other laws, Kepler's laws, if you work in astrophysics, you can derive all those laws just by specifying what this potential is that we worked out in our Lagrangian. Depending on what the form of the potential is, you could get the Coulomb's law, and it's called the Coulomb potential. From this, you can even get the simple harmonic oscillator. From this, you can get Kepler's laws as well. All of this comes from our Euler-Lagrange equations, just with the choice of what this potential is. Does anyone have any questions? Any questions? Oh, cool, easy. Okay, if you want to talk about Lagrangians in special relativity, it's just a simple requirement. You just say, well, of all the possible Lagrangians that you could have, just like, remember, I told you, if I'm just talking about a transformation matrix, right? I could have just my only requirement is that they have 16 quantities. And from that, we constrained it to say, well, no, the determinant of this has to be plus or minus 1, right? That's the constraint. And similarly, when you constrain it, you say that this Lagrangian, whatever it is, right, needs to contain not just x mu, but it has to be a function of this. It has to be a function of p mu, because if you remember from special relativity, we found that x mu itself isn't Lorentz invariant. But if we find quantities that are the squares, which remember is the invariant length S, if we have some Lagrangian that's dependent on the square of these vectors, then that Lagrangian is is Lorentz invariant. So if you do quantum field theory, so I'm sorry, the only Lagrangians that come to my mind are in QFT. Or if you're more comfortable with electromagnetism, you find that Maxwell's equations, right? When you write them, considering how do you write another theory, keeping it relativistic, the starting point of writing any theory in SR is to define a 4-vector. If you can't define a 4-vector, you don't have a space-time to work with, you don't have a length that can be invariant, which means the starting point of any theory being Lorentz invariant has to be a 4-vector. And you find that in Maxwell's equations, when we work with the electromagnetic, the vector and the magnetic field, right? These are the quantities that we work with. We find that we can actually, just like how energy can be written as a function of, well, velocity and position, right? We find that these two can be written as the 4-vector of electromagnetism, which is what we call the photon. And this photon depends on a scalar, just like how you had time and x, y, and z. You have this photon depending on something called a scalar potential and a vector potential, which is A. That's what we call it. And so now if you have this thing that we call a photon, this photon is something that now that changes when you have your Lorentz transformation, which then means that the the equations that you want to be writing in when you want to be writing Maxwell's equations, you need to look for something that looks like this: a mu, or equivalently a squared. And it turns out you can learn this, and we can do this together if you want to. But when you try to write the electrodynamics in terms of this 4 vector, you find that all of Maxwell's equations just simplify to 2 equations. There are just 2 equations that all of Maxwell's stuff can be written as. Like all of the various like ugly stuff that we write, if you start to write it as a 4 vector, it reduces to just 2 equations. And those 2 equations uniquely tell us what the electromagnetic field is and what this is. So if you wanted to know what the Lagrangian for this is, it looks like there's a factor of 4, f mu nu, which immediately should tell you, hey, I have contracted indices. This thing at the end of the day is a scalar. If I had a theory which looked like this, you say, no, this is bad. This is a vector, right? And immediately, so if a scalar is something that doesn't change under a transformation, this should also tell you what a tensor is. A tensor is just, you can think about a tensor as something that mathematically either takes one vector to another vector, right? Remember, our Minkowski space was nothing other than a tensor. It was a metric tensor that took a row vector to a column vector. Another way you can think about a tensor to be something that requires 2 Lorentz transformation matrices, 1 for each index. That's another way. And in the future, if you're interested in want to work in quantum mechanics, you find that the first thing that you can transform with the Lorentz transformation matrix isn't a vector. This isn't the most fundamental or the simplest building block of it. Instead, there's something that we call spinors. And a spinor is actually the first fundamental quantity that transforms under a Lorentz transformation. And you find out that a vector is actually made up of 2 spinors. It's actually called the half-half representation of the spin 1 representation of the Lorentz group. So that's stuff for higher and further study. What I'd urge you to do is when you go speak to your professors, whatever you learn next, and the takeaway from the session should be whatever you learn in the future, whatever lesson in physics, whatever law of physics, whether it's in astrophysics, you're looking at, let's say, radial velocity, right? The first question should ask is, well, velocity with respect to whom? Is it us in the sky? But how does someone in maybe a rocket ship, think about that velocity? That's a question that needs to be answered. If you're not doing astrophysics and you're doing electromagnetism, remember, ask the same thing on how would you represent the same thing to an observer that's upside down on the ceiling? And you start to find that when you ask these questions, traditionally in electromagnetism, there's no answer for it. It's only when you represent it as this 4 vector. In quantum mechanics, it's even worse. You don't even begin to talk about observers apart from measurements. So the goal really should be to try and unite the truth of the world, special relativity, with a formulation of electromagnetism, a formalism of quantum mechanics with this. And when you try to unite the two, you often find that there are potential complications with this. And if I could take 1 last minute of your time, it would be that if you talk about phase space, like we said, where one is position, right, and the other is momentum, it turns out when you try to interpret this quantum mechanically, that's where the problem comes in, that there's no state that you can define with both the momentum and the position. Because in quantum mechanics, what happens is that these aren't just variables, but momentum and position themselves become matrices, right? They're operators. When you say operator, you think matrix. So if position and momentum themselves are matrices, how then can you talk about position and momentum simultaneously? And when you try to answer this question, that's where the Heisenberg's uncertainty principle comes from, that it's impossible to simultaneously, mathematically, the answer is that remember I said there's a similarity transformation where you go up to your friend on the ceiling, ask how do they look at the world, and then transform back. It turns out that this sort of a similarity transformation, right? You can't do one simultaneously for both position and momentum. You can't apply the same matrix to do both. And that's the fundamental problem, that someone on the ceiling, when they look at a particle's position and momentum, like regardless of measurement, right? There's no concept of a position or a concept of momentum at the same time. It just does not have a definite definition. So in quantum mechanics, that's probably the least understood concept, that it's not a problem with measurement, the uncertainty principle. It's that fundamentally the particle does not have a position and a momentum that we can write out in this phase space diagram.
Like, can't we make a space for the functions? Like, since in quantum mechanics, position and momentum themselves become functions, so we could just plot out the functions, the way the function devices at different parts or different time aspects in this.
Good question. Here's the problem with that. So in a space like this, I've actually assumed that it's a complete space, that there are no holes. There's no hole here that you have to kind of avoid and go around, and if you hit it, like, bad things happen, right? It turns out that when you write operators, right, for both momentum and position, the problem is one of them can form a complete set of states. The other can also form a complete set of states, but unlike classical mechanics where you can write down this kind of a theory, it turns out when you try to describe it in a phase space, there are many holes. And the only common, position and momentum that particles agree on is zero. That's probably the only overlap that you have between momentum states and position states. There's just no common, the word for it is eigenbasis. The only common eigenbasis that you have is trivial. It's called, it's the ground state. It's the vacuum.
Okay.
There are also other fun consequences of the uncertainty principle for future study, which is that I forget how to write down this equation off the top of my head, but I know that with the position and momentum, there's a way to formulate this in terms of the uncertainty with the energy, right? I forget the exact relation, but the idea is that when the uncertainty in the position eigenstates of a particular particle change, the uncertainty, the energy as well changes. Right? It's the equivalent formulation of this thing. And the idea is that if you zoom in really, really close, like you look really close to a quantum particle, and you ask, you really dive in and you say, okay, I know for sure, like, this is what the position is. It turns out that the uncertainty, the energy, okay, is actually greater than mc squared. And when it's greater than mc squared, the thing that the fundamental axiom of quantum mechanics that breaks down is that here you can now have two particles. You can have one with some energy mc squared and another with some other energy, and the total of that, is it's greater than let's say 2. So the idea is that when you have that kind of uncertainty, the concept of having a well-defined single particle itself breaks down, and then you have to start considering what's called a multi-particle state. And that realization is something that leads to quantum field theory. So there's a lot I can speak about different other concepts in physics. But do you have any questions today about the two parts? The first is the Lorenz transformation, and we just saw the first constraint, which is that the determinant needs to be 1 or minus 1. And the second half of the lecture, which was the Euler-Lagrange equation of motion. And you really, at the end of this, you should feel like a god. Like Newton, who pulled that equation as an axiom, you've now got some formulation of the world in which you can say, actually, there's a more fundamental truth to that. Right? And that's the subtlety that, again, I don't understand why it's taught in school, because pendulum problems now, whenever you go to college, are so mind-numbingly simple, because it's not a question of finding out where the various different forces are, but it's just trying to find out what's the function for the position, what's the function for the potential, and then just blindly plug it into this Euler-Lagrange equation. And if you do that, you get the equations of motion. It's that simple. Any questions?
It's like when we could have what is the thing called, that the Leibniz integration theorem, or differential of a function theorem. Yeah. So that's where I need it's if it's there on the internet, I'll just I'll look at
it's definitely on the internet.
I'll just get in touch. What?
Yeah, it's on the internet. I can link you to resources. There are tons of videos on YouTube that do this. The reason I thought I'd walk you through the calculus and variations is because when I first did it, so guess what textbooks do? When textbooks come to that stage here, let me show you here. Yeah, when you get to this point in any textbook, okay, here, what they say is, we've just done the integral by parts. And when you've done the integral by parts, this is the final equation.
Okay,
and you're just left wondering, like, where, what, how, right? So this is why I wanted to show you what this is. So, any other questions? Okay, good. If there are no other questions, I think we can call it for today. It's almost 7 o'clock already. And if you have any other doubts, you can send me a message on WhatsApp.
Yeah, okay. I just need to understand, like later on, not now, obviously, because of the time, that how this calculus variation works when there are two or more sets of constraints involved. Like how this calculus variation works.
When you have more than what? Okay, we can continue the
Constants.
conversation on WhatsApp. Constants. What kind of constants?
Sometimes energy, like if I'm introducing a system, then like if there is an energy constant or there is a momentum constant, how I'm going to like generalize the system or formulate the system or formulate the equation, this Lagrangian function.
I mean, the first thing is to note that any constants that you have in addition to this Lagrangian fall out because of this, right? Like you're finding the derivative with respect to x and x dot. And the point I've tried to start by saying is this is important, this bit here, which is to say that before you talk about the Lagrangian, you need to first define a phase space. And it's not important, or it's no use talking about what the Lagrangian is unless you have a phase space in mind, which is answering the question, what's the minimum amount of information that you need and what kind of observables do you want to be talking about? So you can even talk about this not in terms of the position of momentum, but something else. So that's your prerogative to work with. But you quickly find out that there aren't that many 4 vectors that you have available to work with. There aren't that many invariants that you can build. And that's kind of the beauty of the physics, and that's kind of why it's called the Lorenz transformation, for example, because there aren't that many 4 vectors. You probably have maybe 5 in the entire universe. And if you can find a new one, that's the start of a new theory. So that's kind of why it's important, that the really important Lagrangians that are invariant on the Lorentz transformations, that move between quantum and classical, that we don't have one. We don't have any Lagrangian that has meaning both with quantum mechanics and classical mechanics. There are Lagrangians that work really well in general relativity. For example, the Lagrangians of black holes, right? Actually describe Minkowski spacetime when you're far away from the black hole. Automatically, it's inbuilt. Some Lagrangians have Newtonian mechanics built into it, which is to say that when you take the speed of light to be infinity, it reduces down to Newton's equations. So that's kind of what I was hinting at. But any other questions with what we've spoken about today? Okay, good. If there are no questions, send me messages if you'd like to talk about something individually, and I hope you liked the talk today.
Yep, very much.
I'm happy to give you guys loads of proofs and exercises. An example for that could be you could work towards finding your own Lagrangians and working to see what the equations of motion are. And it's a good exercise to see if you use Newtonian mechanics, whether that would spit out the same answer. In relativity, the proofs come under the question of finding frames of reference, which is that prove to me that any object with a mass can be described by a 4 vector of this form. Prove to me that any light vector has to obey this particular form. There are lots of proofs and lots of questions that I can ask you to think about. I'm happy to post different problem sets as well. Just from what I spoke about as well in the rest of the physics, what concepts what would you like to see in the future? Like, there are so many ways to branch out from what we spoke about today, but remember that special relativity isn't the be all and end all of physics. To treat relativity as the second law of thermodynamics. And remember that in the future, whatever theory you come up with has to be Lorentz invariant, otherwise you'll be laughed at. And if you talk about quantum mechanics and come up with a good result, you have to prove why it holds under different frames of reference. And if it's only specific to one frame of reference, that means you've not found a truth in the universe. You've just found a truth to one particular person sitting in a room somewhere. So that's what I'm trying to say. That when you go back to your colleges, ask your professors, prove to me that this is Lorentz invariant. Prove to me that this particular thing that you're talking about is actually an invariant when I look at it from the ceiling, when I look at it from a car that's traveling close to the speed of light. Yeah. So that's the goal. In the future, like these are at the back of your head, you want to be asking why this is the case. And the consequence of not having the Lorentz transformation or having a theory that isn't Lorentz invariant, what's the consequence? The consequence is to say that you have information that's being exchanged faster than the speed of light, which violates that clause. Remember that time being relative means that the sequence of events has to be relative as well. And so you can't have objects in the universe that influence each other, which is the thing I spoke about in the first session, that the observation of the universe which defies all of relativity is the cosmological microwave background, which says that if you look at two bits of light from close to the Big Bang, the time needed for them to have been in contact with each other is some 40 billion years, like much longer than the timeline that we have for the Big Bang. So that's another problem that you can express.
Could it be a consequence of quantum entanglement? Like
No. Has nothing to do with quantum entanglement. It just tells you that there's something wrong with our picture of the Big Bang, the theory.
Okay.
Rather the cosmological evolution. It's not the solution to it is something called inflation. But understanding why that's true is a great exercise on its own. So again and again, I'm seeing from everyone that you're interested in GR, despite my best efforts to push you towards quantum mechanics and particle physics and field theory. So if GR is what you like, then we could do a session on GR. What I'm trying to say is that like when you're trying to do quantum mechanics, while it's fun, doing quantum mechanics when you have quantum field theory is like the equivalent to you doing pendulum problems when you could be learning about relativity, right?
We could set up a base for quantum field theory like in the next session, and then like go along with it also after GR probably.
Okay.
We're fine with either of them. Like whichever, like if in quantum field theory, like if there is a lot of GR involved, then we can also set up a base.
There's no GR involved. If you can unite GR and QFT, you've solved quantum gravity.
Oh,
but
okay.
I'm happy to talk about it. I have to run now, so I'll
All right.
Thanks for being here.
We loved the session. Like it was very informative and very interesting. Yeah.
Cheers, guys.
All right, guys.
Send me a message, yeah?
Yeah.
And thanks for the session.
Yeah, I've got to run, so you guys chat. Text me on the group. Thank you.
Thank you. Thanks a lot.
All right.
Oh, what about you? Yeah. Fixture.